Okay, I think we'll get this afternoon's proceedings underway. So thank you everybody for coming back this afternoon. This afternoon we're going to have 5 speakers from various elements of the Devito community. Our first speaker is John Washburn from Chevron. So thank you for joining us, John. And at the end of the 5 talks, we're going to have a panel discussion to take questions from the floor and understand what the community, how we want to take this community forward. So thank you very much, everybody. Let's get the talks underway.
Thanks, everybody. I'm John Washburn. This is Luke Decker. Alex Loddick is in the back there. Our other co-author, Sam, is not here today, but we're all with the Chevron Technology Center, and Chevron Technical Center, we're going to tell you a little bit about our experience with Devito. So we've had some experience with Devito and we like it, and we're going to give you some of the reasons why we like it. We believe that automatically generated code is the future. And in particular, the way Devito does it with a domain-specific language, where you have a simple description of physics, and that gets translated into high-performance code, we think that's the future. So we also think the ability to target different architectures, and you saw that today with the GPU code that's being developed. CPUs, GPUs, all developed from that same simple description of physics. That's a key way to reduce the pain of dealing with cloud resources. And unfortunately, we don't have a lot of time in this talk, so I can't talk about all the things that I want to talk about, but one of the key things for us moving forward is that everything for us has moved to the cloud. We've gotten rid of all of our on-prem infrastructure, so we're in the cloud now. So these are important things for us. I'm primarily an R&D guy, a researcher, but I've spent a lot of my career doing HPC, going down what I think of as rabbit holes. And the idea is that maybe Devito can free researchers from having to know about high-performance computing and then make them more efficient as researchers. So there's some caveats, and perhaps we'll be able to discuss some of these when we get to the panel discussion. So we have some proofs of concept, and I'm going to show you some performance numbers from those. Hopefully this will generate some discussion in this upcoming in the panel discussion here. So I guess another point I wanted to make is, and I think I tried to make this point today in the CUDA workshop, is the Devito folks write pretty solid code, and you can tell that because you can check the wave fields that come out of these propagation evolutions, and they're the same even if you change these arbitrary configuration. If you can change the way that the code operates and still get the same result. And I think that's an indication that it's robust code. And again, I don't have time to really show you that, but that's something that we believe. So here's just a quick couple points about history. A couple years ago, I started looking at Devito, we started looking at Devito, and we contributed some notebooks that implement our skew adjoint propagators. And you saw one of those maybe if you're in the CUDA workshop today, one of those types of propagators. The response we got from the Devito guys was fantastic. And we decided that we were going to sponsor that consortium in 2021. And then in 2021, they decided they were going to transition from a consortium model into this new open source business model, this Devito Pro open source business model. And well, again, we like it so much that we're going to become, I think, one of their first paying customers. I like to tell Paul the check's in the mail. I think it's, sometime soon. We like the idea of being able to steer maybe the directions that these guys are moving so that ultimately we can target the kinds of production tooling that we're interested in. So the API is going to make it easier for us to do the things we want to do with our production tools. So there's some types of things here that we like about Devito, and I'm not going to have time to talk about all of them, but I think people in both workshops got to see what's called the just-in-time backdoor, where you can inspect the code that Devito generates, and you can change the code, and you can see that impacts the performance, how that impacts the performance. That's maybe one of the most cool things about Devito, and I hope if you haven't seen it, then you should look into that, because it's one of the coolest features. There's some other things, I'm not going to spend any time really talking about these. I've listed them here, things like loop tiling and cache blocking and hoisting temporaries, domain decomposition, translating between MPI, OpenMP, OpenACC, and now CUDA backends. All of these things are features of Devito. If there's time and people are interested, I have some comments about the domain decomposition. I think the way Devito does it is super efficient, and I have some, later on maybe in the panel discussion we can come back to that. On the Devito Pro side, there's a set of features that are exposed by Devito Pro that we haven't really been able to look at yet. Only really one of these in detail and another one sort of dabbling a little bit. And I'll show you the impact of the one that we have looked at. But these include things like the expanding box. Again, I'm sorry, no time really to go into detail. The idea of using reduced precision to represent material parameters, strategies about how data is moved between host and device on GPUs, and the ability to call arbitrary C code, an API to call C functions from this generated code. These are some of the features that are available in Devito Pro. I guess the CUDA backend is also a Devito Pro feature right now. So this is the last word slide, and then after this, there's some pictures that show you some performance results. And I think Luke's going to pick up from me in a few slides, and he's going to talk about this first point here, the idea that you don't have to be a high-performance computing expert in order to realize the benefit of using Devito.
On the recording, they can't hear you unless you step up to the mic or talk into one of the microphones.
Sorry about that. So I think one of the points I want to make, and for me is one of the most important points I want to make in this conference, is that there's a lot of configuration options. Anybody that's done HPC here knows that there's a lot of configuration options. There's communication fabrics, environment variables for MPI. There's the way you do memory pinning, NUMA domains, cache controllers. The list goes on and on. There's a lot of options. And I think of that as like a parameter space. And that parameter space makes it so that if you tune things properly, you can get what I think of as nearly optimal performance. And that exact term was used yesterday. I thought that was interesting. You can get nearly optimal results if you set things up right. And it's hard to do that. And what I put here in red is, I think what this means is there's this big collaborative opportunity. There's this huge opportunity for people that are in this room to work together to make it so that people that don't want to know about these details don't have to know about these details. We saw some of them in particular in that CUDA workshop. We saw some details that probably a lot of people don't want to understand or know how to use. But the idea is that if the community can come up with a way to make it so that those are automatically selected and automatically generated by Devito, then everybody wins. All the people that use the software are going to win. I guess there's a few points here on the bottom that just illustrate what I was just saying. Details like NUMA, for example. Sometimes it's hard to see how these machines are laid out in the cloud. Once they're virtualized, it can be difficult to really get to the root of how to configure these things in an optimal way. And so if you get the cloud providers, the cloud hardware guys like the Microsofts, Azures, and others to work together, we can make all of this happen in a way that's going to work out great for everybody. We're not there yet, but I'm really excited because I'm seeing sort of this is happening. At least, this workshop today was using a piece of Chevron's code, our propagators, and there were a bunch of different people in there talking about how do we make this faster. And for me, that's really exciting. So I hope that continues. The next thing I'm going to do is show you a few pictures of results on CPU and GPU. The first one here is CPU, and in triangles are what I'm going to call relatively high effort reference code. And when I say high effort, I stop short of hand vectorization. Raise your hand if you've hand vectorized any code. I'm sure there's people here. Yeah, you don't want to do that, right? You don't want to write hand vectorized code. So stopping short of doing that, this is a kind of a moderately high effort reference propagator. And those are the triangles. And we have three colors for isotropic, VTI anisotropy, and TTI anisotropy. And then these circles are Devito, sort of the vanilla out-of-the-box Devito, run, again, in a nearly optimal way. And you see that all of these, if you fit a line between them, they're all positive slopes. And there's an interesting thing that as you go to more complicated physics, these slopes are smaller, but they're all positive. So first of all, the simplicity of the code that was used to generate those round points, those Devito-generated points, is vastly simpler. It's just incredibly simpler than the code that's used to generate those triangles. That's one of the points that I think has hopefully been driven home in the couple workshops that we did today. This is Devito Pro. And again, I'll mention that I've only really looked at one feature in detail, and there's another feature that I'm sort of dabbling in. That one feature that I looked at in detail, it's a two-line change of code in the DSL, in the description of the physics, to go from this to this. And you see all the slopes are a little bit steeper. Performance is better for all of these. So that's a story that I think, the picture speaks more than loudly enough. Next, what I'm going to do is I'm going to show you what happens on a GPU. And there's a couple points I want to make on this slide. So you see several points here in the three different colors for isotropic, VTI, and TTI. And each of these points represents the performance for a different selection of parameter options. And we actually talked about one of these parameter, this tiling option in the CUDA workshop today. I guess one of the points I want to make is who wants to really know what these parameters are? Who wants to be the one that chooses these parameters? The people, oh, I guess Fabio wants to, so, okay. Anybody else?
But that's the right person.
That's exactly the right person to, yeah. So one point I want to make is you don't really want to know, you don't want to be down this rabbit hole necessarily. I mean, one of my maybe sort of superpowers is the ability to figure out the best way to do this with all these different parameters, but not everybody wants to do that. The other point I want to make is the same description, the same DSL description, that simple piece of Python that describes the problem, was used to generate these CPU results. Well, this one, the original Devito one, this one with a 2-line change, and this one on GPU. And now if we go from, on this slide on a V100 to this slide on an A100, you see, we realize almost a factor of 2 just by switching hardware. No change in the DSL whatsoever. And I sense I'm sort of preaching to the choir, because everybody that's in this room probably understands this already, right? But these are the kinds of things that you realize when you use Devito. And then the last slide that I have is going from Devito to Devito Pro. And one of the points I was making to Felix Herman earlier is that we now have and I would say this is not nearly optimal yet. It's just a hell of a lot better than it was 6 months ago. We have a 20 gigacell 3D isotropic propagator. And this is in a model that's kind of representable of a kind of an intermediate frequency FWI that we care about. And so I think the future looks great. It's really exciting for me. So the next thing I'm going to do is I'm going to turn it over to Luke. Luke joined us last year, and he sort of just got dropped right in the middle of this problem of port your existing code to using Devito backends. And so I think his experience is really going to be useful for this group of people to hear what he has to say.
Yes, thank you very much, John. So I'm Luke Decker. I'm also part of Chevron's seismic imaging team. And so I'm going to start off with my experience of implementation Devito. So I implemented a Devito-based wave propagation operators for the skew adjoint energy conserving system within Coffee, which is Chevron's open source optimization framework for imaging and inversion. So getting familiar with Devito took some time at the beginning. I wasn't as fortunate as some of you here today may have been to attend that wonderful tutorial that was given this morning. And additionally, making it work well with other frameworks, like Chevron's Coffee was a challenge. So Coffee exists in Julia, and that involved wrapping Devito in Julia, which was extra effort that maybe you don't have to worry about. However, once I understood Devito and how it fits with other packages, development of new operators with different physics was extremely rapid. And that's part of the great power of Devito. So here I'm going to show you a little example timeline. So in June of last year, as John mentioned, I learned that Devito existed. And so I started playing around with toy problems in Python and looking at the wonderful docs on GitHub and examples that lived there. I also then around, late July, early August, I began working on Devito in the Coffee framework and adding features and unit tests to Devito.jl. So if you are interested in using Devito as part of some Julia language software, just look up Devito.jl and it's there for you already. And along with that, I began writing a 2D isotropic nonlinear wave propagation operator and associated unit tests, which took a while. There were setbacks involved with time blocking. Fortunately, Devito Pro is taking care of these things that I guess really took me some extra time. So time blocking, compression, and serialization, you don't have to worry about any of that stuff. But that took a while to figure out. I then implemented the isotropic linearized and adjoint operators and associated unit tests. So there were some, as you can see, I've got a few white hairs now that came from writing the first adjoint. But
Bill Symes used to say every white hair on his head is from the implementation of an adjoint.
I can't blame them all on adjoints. I just had a son, so a few of them are from that. But anyway, this is the power of Devito. So I implemented the 2D and 3D isotropic VTI, TTI, nonlinear, linearized, and isotropic and adjoint operators, complete with unit tests in a 2-week period after my first 2D isotropic operator. So, I mean, if you start getting down into like low-level code in a high-performance computing setting, like that's not realistic. And so this is the real power in my mind of Devito, is once you get this familiarity with it, development is extremely rapid. And so let's talk about flattening the learning curve, right? You don't have to climb this mountain of Devito roadblocks that I may have put in my own way. So learn it from me, I guess. So move from simple to complex, right? So incrementally add features and check different ways of implementation to see what is most performant. Handing Devito a complete expression and letting the package figuring things out for you usually works best. Intermediate equations can kill performance, so don't try to be too clever with these. When I was doing time blocking and serialization, I was getting too clever, and it killed my performance. Don't do that. Just hand Devito complete expressions. Let Devito be Devito. However, equivalent mathematical statements can really boost performance. So this is where you should expend your effort with being clever. So for example, with like the wave equation, you have a time side and a space side of it where all the derivatives can live if you rearrange it correctly. And they're equal to each other. So choosing which side of that equation to use can really change the performance that you get. For example, with Born injection. So entering and exiting Devito operators to perform operations like serialization also kills performance. So avoid this if possible. With Devito Pro, there's this feature where you can hand it C expressions. So that would be better than entering and exiting an operator. Furthermore, we've talked about the JIT-backdoor. So examine the generated C code for insight into where your performance can improve. Now, this is what I love about Devito, is that it's only as complicated as it needs to be. So Devito and SymPy can simplify complicated physics for you. As you see, we've got this cute little cat here and then this simplified version of it. So users can focus on writing mathematical statements and letting Devito figure out the most efficient way to perform them. The clever use of Devito constants and functions. So there's these different objects in Devito. You can hand it a constant or you can hand it a function. And that means that you can write one operator that represents more complicated physics. So in the case that I've been working on, like TTI anisotropy, for example, and Devito will generate more efficient code for simpler situations if I tell it that certain parameter fields are actually constants and not functions that represent arrays. So you don't even have to worry about like, oh, I want to write like a constant density operator. I just tell it density is a constant and it figures it out for me, which is just phenomenal. And no getting into the HPC and low-level array computation weeds, which is just a godsend. You add MPI with a configuration flag, which is just phenomenal. So that's my experience with Devito. I think, who's going to talk about the future? Okay, so in the future, Chevron is in the process of porting our production propagators to use Devito. We expect this can free us from significant maintenance time for developers. So we just have to worry about writing in this DSL instead of maintaining the code and writing it for different architectures. Testing new Devito API functionality for compression and serialization on CPU and GPU is available. We're excited about that. Incorporating Devito Pro features into our code base. So now that we see all these great tools that we've been handed, we're just so excited to use them. Instrument automatic benchmarking and parameter tuning aimed at selecting the most cost-effective use of the Azure cloud. So possibly utilize what may be coming from Microsoft. And research and development of new ideas with the Devito backend. So I think that, for example, with this, we have one formulation of our skew adjoint wave equation propagator that we've implemented, and there's actually an equivalent formulation that uses slightly different parameters that we're excited to try out and should be relatively trivial to implement with Devito. So we're extremely excited about that. In conclusion, ultimately, Devito will make it much easier to do research, to introduce new types of physics simulations more rapidly. All boats float higher when the back end improves. So compare that, like consider old hand vectorized code using AVX instructions, and you'd need to completely rewrite that for AVX 512. Developer effort should taper off after some initial steep learning, followed by rewards, which was my experience. Oh yeah, and maybe you could cover these.
So, yeah, hey, my name is Alex Lodok. I'm the HPC counterpart to what John and Luke and a couple of others doing. I used to write this kind of code. I used to be in the weeds of that in CUDA. I wrote our first RTM code. These days, I guess John expects me to write checks rather than code. But so I kind of know the flip side of that, and yes, I do enjoy that. But I also enjoy this very much. So what are, kind of in the interest of setting up the panel discussion later on, yes, some of these comparisons that we're doing here are not really fair, right? When you write code, you often write it for a specific purpose and you optimize the crap out of that specific solution versus this is a perfect tool to get you to, well, near optimal code or optimal code very, very quickly without having to take all kinds of things into account. Especially in environments, and John alluded to that a little bit, where you do not know, as a developer, do not know all the details that you have to know to write really good code. And yes, cloud is one area like that. Or if you just don't have that knowledge or you can't care about that knowledge, that's where Devito comes into play, because at least there's a hope that folks like Fabio and other folks at Devito have done that work for you, and you can just leverage that work without having to do much. I know that's a bit of an idealistic perspective, but in general, that is possible. We've seen that, right? So a key thing is question, I guess that's one of the provocative questions, how can we make sure that Devito is more than just a one-trick pony, as we call it here, right? How can we make sure that it's not just running on one particular piece of hardware, not just on one vendor, be that a hardware vendor or a cloud provider, one generation of that, or for just one type of code? I think that is going forward a very important part that we need to make sure. Then another thing is, what about more esoteric hardware, right? John showed results from CPU and GPU that are readily available, and everybody knows. But what about other things? I'm not sure put the T4 on there, but well, even this conference, we all saw a wide range of more esoteric or unusual hardware. Is that a way where Devito could, or is that a field where Devito could play and help us adopt that hardware? And if so, what's necessary for that? And then the question is, what else do we need? Devito produces a kernel, at least today. I know that's an oversimplification, don't get mad at me, but that is at least what John talked about, right? In order to deploy an application in the cloud, in cloud native way, or even on premise, it takes a whole lot more. What are we missing? What else do we need from either from Devito or from something around Devito to make that more than just a kernel generator? And I know it is more than a kernel generator, but kind of in the spirit of the birds of a feather that we had yesterday, kind of same angle there. Again,
That's chat.
yes, let's chat, please. Yes, and again, that's what this is for, priming questions for the panel or for the discussion afterwards. And with that, I'll shut up. Thanks.
Okay, thank you very much. So thank you very much to John, Luke, and Alex. And if you can hold your questions until the panel discussion, but do think about those. We've now got Chris Leader from Schlumberger, our second industry speaker. And so he's going to give us an introduction to Schlumberger's experience with Devito.
Okay, good afternoon, everyone. So yeah, Schlumberger and Devito, now more a perspective from an energy services company, a company that creates and licenses software. And more specifically, these are experiences and conclusions from 3 intern projects. So my name is Chris. I actually did my master's in Imperial back in 2008, so I feel a certain allegiance towards the Devito team in that regard. Since then, I spent some time in academia doing as a research geophysicist. I started off in Schlumberger in our innovation center, general HPC stuff when I was maybe a quarter on geophysics. And now I just transitioned back into more of a full-time geophysics role, where I'm now HPC geophysics technical team lead in our geosciences technology center. So, rough agenda. What are seismic services at Schlumberger? Who is Schlumberger for the few of us who don't know, and why is Schlumberger interested in Devito? And then I'll talk subsequently through each of our intern projects chronologically, our findings from these, and where we may be going in the future. So, seismic services at Schlumberger. I figure everyone's probably aware of what we do as a company, but I'll just spend 30 seconds lest I leave anyone behind this early in the presentation. But Western GECO is the seismic acquisition and processing branch at Schlumberger, and we're responsible for all of Schlumberger's seismic activities and business, such as data processing, imaging, survey design, all the way through to these borehole multiphysics. Everything that touches seismic data, Western GECO is involved, and HPC is a fairly critical backbone of this. And we also have one of the largest multi-client data libraries in the world, which we licensed. That was one of our larger assets. And these are just some geographical imprints to show you where a lot of these data are based. But now more specifically, seismic processing and imaging at Schlumberger. What do we do exactly? Well, we have a suite of highly optimized geophysics algorithms and engines, interpolation, model building, imaging, everything from old school Kirchhoff time migration all the way through to the best anisotropic RTMs these days. And these software packages are run internally at many scales of compute, from the single workstation to tens of thousands of cores. Furthermore, these software are licensed to energy companies who then run our codes on their own hardware. And these can be older vintages, newer vintages, cloud, on-prem. So it behooves us to maintain our software stack to work on these wide variety of areas. In terms of HPC and GPUs, we've worked closely with Nvidia ever since CUDA was incepted in 2007, particularly on high throughput wave equation kernels and computationally heterogeneous imaging approaches, to the point when back when the main use of GPUs were workloads like seismic processing, we actually helped guide the design of the Tesla K10 about just over 10 years ago. In Schlumberger, we have a very large internal computational infrastructure. But as we've heard from many other vendors and many other companies around here, we are slowly shifting towards more cloud-based workloads, to the point when historically, just history being the last 5 or 6 years, we've had colossal deployments in Google Cloud, petabytes of data, tens of thousands of virtual CPUs, thousands of GPUs. We're now publicly working with Azure as well. And so what's also modeled in with this, and where Devito can help, is with the current cloud transition, price performance of hardware is now a critical business enabler when that wasn't necessarily as much of the case in the past. So that should set the scene for Schlumberger, now Schlumberger and Devito. Well, we first kind of became aware of Devito in the 2018 SEG. I remember being in the workshop on Thursday or Friday with Gerard presenting. And the attractive prospects for us are the same as they are for everyone, in so much as we can automatically generate CPU and GPU code close to optimally, and have these finite difference kernels created for us. With this, there's the potential to decrease hand tuning of software, and in particular, these architecture-dependent implementations. Furthermore, there's now a simple Python interface for doing this debugging and testing, this quick prototyping, okay, I have a new idea for physics, I want to inset my idea as soon as possible, hence diminishing development time and increasing research opportunities. Now, where Devito may not fit in with Schlumberger is it's unlikely to replace our suite of hand-optimized GPU kernels that we have for a wide variety of hardware permutations for the last 10, 15 years. However, there are 3 places where it could be very, very critical. One of these is it could likely provide a valuable research tool for quick algorithm development. We have a more geophysically minded person at the company than someone who's familiar with our seismic processing suite, and they have these amazing ideas. It's a faster time to prototype. Furthermore, there's potential value in the fast creation of finite differences, different kernels or wave equations for things that haven't yet been internally developed. Say a client comes along and they have this amazing triclinic matrix of anisotropic parameters, and we want to quickly propagate through this or extrapolate the wave fields, or we want to do an HTI job, but we don't have that in-house yet, for example. Well, this would be a fast route to success. Furthermore, this proliferation of alternative hardwares, even things like AMD and Intel GPUs, all the way through to the slide that Chevron was just showing. Well, if we want to quickly become somewhat optimized in alternative hardwares, this could be a quick route to success as well. So now let's talk about what we've actually been doing in Schlumberger and some of our experiences. Well, back in 2019, we had Ettore come and do a project with us. He is now a postdoc at Caltech. And the goals of this was the initial exploration into Devito. So we wanted to ascertain how easy it is to quickly create acoustic and TTI propagation kernels in 3D. And of course, that's only part of the problem. How easily can we integrate what we consider standard grid optimizations to enable a more fair comparison, things like variable depth spacing? And then, of course, we want to do a rough performance comparison to an existing CPU kernel we had in-house. I'm not going to spend a whole lot of time on the performance aspect, just because it's always hard to make a valid comparison, especially for something that was relatively dormant in Schlumberger at the time. But I will show our experiences with performance. And the motivation here was simply, an initial understanding of Devito's capabilities and drawbacks, and how easily can we implement these non-finite difference aspects of the imaging workflow, because we took it on face value that it could give us the stencils correctly, but how could we do the rest of the feature set, or how could we implement those things? So let's go with a couple of pictures, or pictures of code. What was really cool was a TTI kernel in 15 lines. I don't know if any of you have coded TTI before, but it's usually a lot uglier than this and a lot more than 15 lines. And especially because here we're also defining some of the absorbing boundaries. So this is really cool that in a matter of days we had, a matter of a couple of weeks, let's say, we had a TTI kernel developed, and it looked as simple as this. And then when it came to some of these other standard grid optimizations, we looked at a few things. We were looking at variable grid spacing. We looked at expanding box, but that ended up not working out in this project. But we used conformal mapping to do variable grid spacing, which is a fairly standard optimization we do. And this ended up giving a 1.4x speed up. And this also looked relatively simple to express in a natively Devito sort of way. So now some hand-wavy conclusions about this. We didn't really have a definitive CPU benchmark because we were GPU focused for 15 years. What we did have was a dormant CPU kernel that was written around 2010 that had some optimization applied to it. But the main focus here is in terms of equivalent effort, especially for an intern. Devito was a much faster way to initial success, especially since hand tuning of CPU kernels is very time intensive. Including variable depth grid spacing was relatively straightforward. And in terms of performance, once we had worked out the right way to propagate the vectorization flags all the way through to the compiler, we saw a huge uplift, and we ended up seeing the performance of about 1.3x relative to our in-house kernel. So pretty close to performance parity in terms of something which was optimized several years prior, which was a pretty good result, I think. And at this point, the GPU maturity was not yet fully developed. And so this was 3 years ago. Now, we had 2 interns come to my old center last year to work with us. This guy, Milad, we looked at TTI modeling and imaging, and then we also wanted to look at some of the strong scaling GPU performances in Google Cloud. This one, he also had a baby halfway through the internship, so he didn't do quite as much work as we were hoping to. But the goals herein were implement 3D TTI reverse time migration using Devito. With a Torre, we were just looking at the propagator and some grid optimizations. Now we were looking at the full imaging with the GPU too, so wave fields back and forward, imaging conditions, and then actually, seeing an image. We wanted to validate some of the strong scaling claims for single host multi-GPU paradigms. So again, I don't think performance is really the main focus of this presentation, but we can see over here kind of the evolution of single CPU to 4 CPUs to OpenACC, single GPU, OpenMP, single GPU, and multi-GPU paradigms. And what we do see is, it's not really a surprise that multi-GPU OpenMP doesn't perform particularly well. We do see that OpenACC, we suddenly do trigger a pretty serious performance increase from these. And I think one of the main success stories in terms of performance in this regard is more from down here, particularly looking at single V100 to do 2 V100s, single A100 to 2 A100s. We do see an almost exactly linear speed up with the number of GPUs used, which shows the communication and computation overlap and all those things you would hope are being done with the halos correctly, do seem to be working correctly. And so, yes, we ascertained that we're getting decent performance on the GPU, it's scaling correctly, and we did some price performance analysis too, but that's not particularly interesting for this presentation. We also did a small amount of Nsight profiling on this. We saw a lot of detail of that this morning. And this shows that we're keeping the GPU busy. we see a small amount of downtime when we're moving the snapshots back and forward from CPU to GPU and back again. And then in the imaging phase, we see the same thing, but when we're moving the wavefield snapshots back in and imaging. So this does show that Devito is keeping the GPU busy. Some conclusions from this project. The implementation of the 3D TTI RTM was relatively straightforward. I think he had this working in maybe 3 weeks. GPU offloading with OpenACC gave a significant performance boost, and close to linear speedup was seen from 1 to 2 GPUs, which was a good validation. And because these internships were more recent, I just asked them a couple of weeks ago, what did they find particularly useful about Devito and the support mechanism, and what could have been improved? And I actually haven't told Gerard yet this, so this is new. So they said that the Slack support was very, very helpful. Milad thought that a forum would be useful as well, maybe to augment or to replace that, so you could look up existing questions, maybe categorize historical issues, and look those up quite quickly. He said the abstraction of differential operators is great, which is good, because that's kind of the mandate. But he struggled with some of the classically more simple things like source injection or receiver extraction and getting those working quite correctly. So that was this project. Now, this third project, I think, is probably where it gets most interesting to Schlumberger right now. And this is innovative imaging conditions. So this, in turn, was Rustam. And the goal in this project was how easily can we implement atypical or maybe innovative imaging conditions relative to our enterprise seismic processing software. And I think the main motivation here, really the main motivation of our whole interest in Devito up until this point, is that rapid experimentation in optimized enterprise software is rarely rapid. It can be quite slow, especially for an intern, because they have 12 weeks to try and work on a project with us. And if Devito can be shown to provide this algorithm validation in this time frame, then we can conjecture it will be of huge benefit for future research projects. And the actual imaging condition we were trying to work on in this, I'm not going to talk about, A, because maybe we'll patent it, and B, that's not really the point of this. The point is we had an intern with no experience in our processing software stack. Were they able to validate our algorithm implementation in this time frame using Devito? And the answer is yes. It was a resounding success in that regard. Setting up the wavefields and the standard imaging was easy, offloading the classically hard part. And this allowed experimentation for the fun part, wavefield shifting and weighting and binning and all these ideas he had. He was able to really quickly validate some of our ideas, and that was really cool to see. And so kind of the main point here, maybe the main point of the presentation, was that Devito proved to be a very flexible tool for custom imaging with almost no experience in the company. The initial validation of the concept was successful within a 3-month internship. The intern himself, his conclusions about working with Devito, again, the Slack responsiveness was excellent, and it was also very encouraging seeing an active community. It wasn't just our 2 interns, pinging Fabio in this channel. It was a whole lot of other people in different companies all taking an active interest, active experimentation, active development work with the Devito engineers. He found, again, the classically difficult components, like wave propagation and tilted coordinates, was easy to perform, but some of the classically simpler components, like linear interpolation, it actually took him more time to get those things working than the wave propagation. But that's probably a price you pay for abstraction, right? It's all about this trade-off. So to conclude, back to kind of what I was saying at the beginning, a primary component of Schlumberger's competitive edge is in these finite difference algorithms, which are optimized for high throughput. So at this point, it's unlikely Devito are going to replace these hand-optimized kernels we've been developing for the last while. Future hardware, we can see where that goes. In terms of an equivalent effort comparison, in terms of writing CPU code, Devito has a really strong advantage because we could get almost performance parity in relatively, without very much effort. At the point, last summer, OpenACC showed a huge relative GPU performance uplift compared to other things that was provided at the time. It's exciting to see the new CUDA coming in now, and it's going to be fun keeping track of that. And it was really useful to quickly develop new algorithm ideas, which would be really arduous in other circumstances. We have maybe 2 or 3 engineers in Schlumberger who know Omega, our processing software, well enough to have developed this new imaging condition in the conventional development way in the company. Whereas using Devito, we were able to use an intern to kind of validate and test a whole suite of these ideas in 12 weeks. And in terms of performance, I didn't talk about that a whole lot, really because a more in-depth analysis relative to our internally developed kernels is important for these performance comparisons. So I'm more talking about how exciting it is to see how it scales on other hardware and how it can be quickly used to develop new ideas. A few acknowledgements to finish up. Acknowledge the interns, Ettore, Malad, and Rustam, members at my previous center STIC, Schlumberger stakeholders, and especially the guys at Devito for their encouragement and their assistance throughout these projects. And thanks for your attention today.
Thank you very much, Chris. So our next experience of Devito will be shared from Philip Witt at Microsoft. So thank you, Philip.
Yeah, hi everybody, my name is Philip. I guess full disclosure first, so I used to be in Felix's group as a PhD student, and maybe I can claim to be one of the first or early adopters of Devito. So I remember when Matthias went to, he was at Georgia Tech with me, he went to visit Jared at Imperial College, which was supposed to be, I think, a 3 months internship, a trip, and I didn't see him for another 6 months or so, but he came back basically with a prototype of Devito in a suitcase. And I started right away building an abstraction framework on top of Devito that I think is pretty similar to what you guys at Chevron have been building, to actually build an application framework on top of that to enable the research in our group. So yeah, so we've been working on that for a long time, so it's been really cool to see kind of how far Devito has come at that point. But okay, today I'm going to talk from the Microsoft perspective. So even though I'm wearing the Devito sweater, I'm actually with Microsoft and give our perspective. Why have we looked at Devito? What do we like about Devito? I mean, the first aspect why we look at Devito, I think, should be obvious. I mean, if our clients like John and Sam and Luke, you guys are running Devito on Azure, we want to make sure that you guys are happy and that everything runs optimally and help you guys, especially what you mentioned about how do you figure out the optimal setup of Devito. So I think that should be something as we go forward that we definitely need to look at a little bit more. But the second aspect that I want to focus on a little bit more today, I guess, is about the scalability and how do you run this on Azure? How do you scale that up? Because I mean, as we saw in the Chevron and Schlumberger talks, we're not just interested in running a single wave equation or solving a single wave equation. Most of us or of you guys are interested in solving an actual problem, so you have to put a whole framework on top of that solves something over a big loop of data. You're interested in coming up with algorithmic optimizations or innovations, build applications on top of that, like Kofi, like the Judy framework that we built. But then there's obviously a third component, which is where do you actually run that and how do you scale it up? Since I'm from Microsoft, I obviously would like to advertise Azure, but I mean, it could really be anything. I guess it could be an HPC data center. But the question is, how do you take now something like Devito and build application frameworks on top of that, and then how do you actually scale it out in the cloud? And I think there's not one single answer that we saw. So the question is of how do you scale it up in the cloud? I don't think it's necessarily trivial. So this is where Microsoft kind of sees their role to help out at that level. So that in the end, what we really want to come up with is, I guess, the separation of concerns where you guys don't have to worry too much about what's happening on the Azure side. Like Hugo and his team will figure that out. I will help out with that hopefully too. And then the geophysicists among you can worry about Devito and the application frameworks, and the HPC hacks among you can worry about the CUDA backend. Okay, so I think, I mean, where one of the challenges comes in, if you think about cloud computing, is that, I mean, on a cluster or on an on-prem data center, kind of the architecture and the HPC hardware, that all that stuff is fixed. So you're really just looking at the application, thinking about the application, how do I write something that optimally takes care of these other things. But in the cloud now, all of these things are basically wheels that you can turn and you can play with. And if you want to have something that actually really scales, and takes advantages of the opportunities that the cloud provides, like this elasticity or hyperscalability or whatever you want to call it, or all the different hardware that you could get access to, then when you write the application or when you develop this stuff for the cloud, you really have to think about the whole pipeline, right? You cannot just only look at the HPC application. You have to kind of think about the HPC architecture and the hardware all at the same time to really get the most out of it. So one example, I guess, would be, it's not just good enough to have an HPC architecture that's elastic, because then if you have an MPI application on top of that that isn't necessarily able to scale up and down at runtime, then you're not necessarily able to make the most out of this. Yeah, so I mean, where Devito comes in for Microsoft, I guess, is that's just a really cool application that we can actually take and play with and have a relevant application that would be relevant for you guys to actually have something that we can work with and kind of test out these different opportunities or approaches that you can take on Azure. So I'm going to talk about different approaches, how you can take something like Devito and scale it up in the cloud. And I want to talk about three a little bit different approaches, probably two approaches that most people are familiar with. One would be the lift and shift approach, where you take whatever setup you had on premise and you want to replicate that HPC setup in the cloud, and you basically just replicate what you have. You use your favorite third-party HPC scheduler like Slurm or BBS, distributed file systems, all that jazz. The second approach would be, I guess, what you call the cloud-native approach. I don't necessarily even like that word that much because it's not very descriptive. Cloud-native could mean lots of different things, and I don't think it has to mean one specific architecture or one specific service. But in the example that I'm going to talk about, by cloud-native, I mean something more like, rather than having a regular cluster, now you have, say, a Kubernetes cluster, and then maybe instead of doing a loop over shots using MPI, you can swap that out and use something like Dask or Ray that supports a little bit more that elasticity. And then the last thing I want to talk about is looking a little bit further ahead down the road, what I would call the next generation, more interactive distributed computing in the cloud, where you don't really worry about too much maybe about this actual cluster setup. So rather than having this kind of decoupled approach where you have a cluster and you have your application, you just kind of merge that and only think about the application, and what happens on the orchestration side would just be done automatically. Okay. So this is, I think, hopefully in the spirit that Alex was talking about yesterday, where us as a cloud provider, we would like to provide abstractions to you guys to do any of these approaches. We're not going to tell you which approach to take because I think everybody has a little bit different requirements. So there's not one single answer. But what we like to do is put out tools to make it easier, make those available to you. At least two of the things I'll talk about are available as open source today, and the third one here hopefully soon as well. Okay. So I'll go over each of these. And again, Devito was kind of the example application that we work with, and that made it possible for us to really quickly prototype and then test these different approaches. So the first approach I wanted to talk about is I guess the lift and shift approach. So Hugo's team and colleagues, they came up with this really cool platform. It's called Azure HPC On Demand, which is targeting to make it easier for you to spin up a cluster that looks like your on-prem cluster, but also looks a little bit more or takes care of this enterprise level component that Hugo talked about, I think, in the Birds of Feather session yesterday too, where you have to worry about administration. How do you handle that? And that's not necessarily trivial, because now on Azure, even though there are services that help you spin up a cluster, there's still a lot of, I guess, components that you have to put together to also get the administration and the monitoring right. So ZHops does that for you. Again, it's open source, it's on GitHub, you can give that a try. So yeah, so our first example then would be taking ZHops, and this work was done by Hugo and Gareth, and is Alex Morris still here? Maybe not today. So yeah, so we were able to take the Devito kernels, and without really, we can just take Devito, quickly prototype an application, and then scale it up in Azure, and it's somewhat representative of a workflow that would be relevant for you guys. And to be able to do that quickly, I think is one of the big values of Devito, especially for Microsoft. Okay, So from the geophysical perspective, obviously it's not super interesting. We just took like a layered model, but it's somewhat relevant production scale, I would say. And this was now done with the ZHops, so more of a traditional lift and shift cluster approach. Yeah, a couple of milestones. We were able to hit roughly 1,000 of the HBV2 nodes. So this is CPU only. The spin up time is about 10 minutes. It's still a little bit tricky part to how exactly how do you pick the size. Basically, you have to add nodes in batches to your cluster, and how to do that is not necessarily trivial. And Hugo, you can say a little bit more about that, I guess, in the discussion. But we were able to get past 100K cores, which is pretty cool. So not quite exascale, but petascale. And yeah, simulate a medium-sized survey in a couple hours with roughly 4,000 shots. Fault tolerance was also not really an issue here. I guess in RTM it's somewhat easier because you submit shots as individual jobs. So ZHops is able to handle that, or your favorite HPC scheduler that you're using for that. Okay. Then the second approach that I want to talk about is more of this cloud-native approach using Dask or Hyperwave. So really the idea is, I mean, I'm still going to do the same thing. I'm still going to have a cluster, but it's not going to be a Slurm cluster. It's going to be something more cloud-native. So we use Kubernetes for that. This is a project that actually started a long time ago at the same SEG shop that Chris just mentioned. So we wanted kind of to test out that promise of how easy is it to use something like Kubernetes, which is supposed to make things easier. I remember that Jared and his student were pulling out their hair, not sleeping for 6 days, trying to get this working for the workshop. But in the end, they made it work. And then my colleague at Microsoft took that initial work and really boosted that up and was able to apply this to a 3D relevant problem size. Excuse me. So the problem that we're looking at here is a little bit different. So instead of just doing RTM, where we parallelize over shots and submit that at as different jobs, we're running an inversion style workload. So something that you would probably traditionally use MPI to parallelize over the nodes. So in that case, fault tolerant is a little bit more difficult because yeah, now you don't just have separate jobs that you submit, but excuse me. Okay, so one of the cool things that you can do, I would say, with AKS is the fact that, so now again, at the top here you have Devito in combination with Dask to do the task parallelism. One of the cool things that you can do with this setup that you cannot do with the lift and shift approach is that you can combine multiple clusters. So in this case, we had two Kubernetes clusters that are distributed over 2 data centers, and you can even put those on different continents if you wanted to. Not that you necessarily should do that. It's more that, say, if you run out of resources of your favorite node, you could go to a different data center and get those nodes from there. And that's not something you could easily do with the lift and shift. Yeah, in terms of scalability, we were able to hit about 6,000 nodes with over multiple classes. I'm just showing 2 here, but it was actually 6, I guess. And the fault tolerance in this case came through Dask because Dask is able to handle the fact that nodes are coming and going here. And then, yeah, then the dynamic reduction of the gradient, that's something that Dask is really good at because you can define these DAGs where you can do that pretty effectively and also fault tolerant. Okay. How much time do I have left? Okay, so we did a 3D FWI run with that. I mean, it's probably not quite production size what you guys at Schlumberger are running, but it was still over a terabyte of data, roughly. This was on a little bit smaller setup, I guess 6,000 VMs per cluster. And there's a movie of the 3D FWI run. Okay. And then the last one I want to talk about is what I'm a little bit excited about is this idea of serverless computing. Because in the case 2, you still have this dichotomy that I said. You have an HPC cluster that somebody has to spin up and create, and you have your application. And even in the example of Kubernetes, I mean, I don't know who of you has used Kubernetes, but it's not necessarily as easy as they make it sound sometimes. No? Yes?
Amen.
Disagree. It's definitely application dependent too, right? So for every different application works a little bit different. I don't know who enjoys writing hundreds of lines of YAML files, but that's your life if you're a Kubernetes
No, you
guy.
auto-generate the YAML.
That is.
We need a DSL
Yes.
to generate YAML files.
I think so. But then the idea, I think that is maybe straightforward or appealing at least, is this idea of serverless computing, right? Like AWS Lambda or Azure Functions, where you just write some code, you uploaded it, but you don't really talk too much about how or whether it's actually going to run. So I mean, it's not straightforward to use that for HPC workloads. Certainly AWS Lambda is not really there for that at all, because I mean, there's all kinds of reasons. Same for Azure Functions. But if we would have something like that, that would support all the HPC requirements that we have, but still be something that's fairly high level and you can do stuff interactive, that'd be really cool. And I think the work that John and Sam are doing with Kofi actually goes in that direction already. So I think that that's pretty cool. And the work that we did is kind of along those lines as well. So yeah, so this one I talked about, kind of the traditional setup is a two-step process. Somebody spins up a cluster for you. If you're lucky, you work for Schlumberger or Chevron, you have somebody who does it for you. If you're in academia, you're kind of on your own. So that probably takes you already 4 weeks on Azure to figure out how to do that. And maybe I shouldn't say that. It takes you an hour. But yeah, so you do that step first, and then the second step is you write your program, you use your favorite distributed programming model, and then you run that on there. Whereas this where we would maybe like to go is you don't worry about that part at all. You have an application where you have a distributed programming framework that maybe works a little bit different, but gives you the same very high level macros or statements, and then you're able to write a program. And then you can run that program really anywhere, on your laptop, on your phone if you wanted to, on a single cloud instance, from an Azure function, it doesn't really matter. And all the resources that are required from your program at runtime, your program will just get that from the cloud automatically, and you don't really have to worry about that. I don't know if you can really see that here. That's not playing.
Don't move too far away from the microphone or the recording.
Oh yeah, I already screwed that up probably. Okay. Okay, so this is a prototype that we built that basically does that. That's called Redwood, even though I had to name the package Azure Clusterless HPC because Microsoft asked me to make the package name descriptive, unfortunately. So I don't know how well you can see that, but the idea is that you basically have a distributed programming framework that just looks like native Julia, and you're able to quickly prototype or implement a function. You could just call that function directly, and it would just execute that on your laptop. Or you can decorate it with one of those macros and say, just execute that function remotely on Azure. And then that's what you see here. So it's executed through a batch service on Azure. It's called Azure Batch, which is one of the first-party HPC schedulers that we have available. So I don't know if I can replay this. Maybe not. Okay, we'll leave it at that. And the idea is really that I would like to think of Redwood, which is what this framework is called, as kind of an enabler that sits on top of Azure Batch, kind of hides some of the complexity for running these things on Azure. And then you build your application framework on top of that, whether that's something like Kofi or Judy, which is what I built at Georgia Tech.
No YAML files.
Well, we could talk about that. There's still a YAML file. I don't think I'm with this quite where I wanted to go. So eventually, I think there shouldn't be a YAML file. Right now, there's a YAML file that has a couple lines where you say how many nodes, how many pools, and what kind of VM. I mean, even AWS Lambda is not really serverless because you have to tell it how many cores to use, and you don't get to choose the SKU. So it really, I could just ask you here how many cores you need and just give you a random SKU. So I mean, it's really, I guess, the discussion of is serverless really serverless, and what should it be? But that's maybe something for the discussion. But yeah, but I did try this out with both the coffee framework from you guys and the framework from Georgia Tech. We've seen that. Yeah, so since I wrote this in Julia, and the motivation to write this in Julia was actually because of you guys, but also because of Felix's group and the framework that I had initially written at Georgia Tech. So for the Kofi framework, I was able to take you guys' code. I just stole one of the notebooks from the repository and replaced these high-level macros that are native Julia with the ones that Redwood provides for you. So rather than having to spin up the scale sets, you could run a Kofi example through Azure Batch. And I think I modified one of the 2D examples to run a 3D RTM on about 4,000 VMs. Okay, to be honest, this was not using Devito because Devito.jl was still in development at that point, but I'm waiting for Luke to get that done, and I'm going to rerun that example for sure. But yeah. No pressure. Let me know though. And then the second example was Judy, which is the application framework from Felix's group that I started working on, and now Matthias is maintaining that, which is really nice of him. Yeah, but I mean, I don't know if you guys seen Kofi, but I mean, it's similar. The idea is that you hide even all the complexity of writing a wave equations, and you just express everything as a linear operator. Because if you're maybe an optimizer, all you really care about is linear operators. So you could write your forward problem as just a series of linear operators that operate on a source queue. But what's cool here is that even the parallelization on Azure and the orchestration on Azure, everything is hidden in these linear operators. So this is built on top of the framework that I just mentioned. So you just write one line of code to simulate, I don't know, 10,000 shots on Azure, just like that. And then if you want to do the corresponding image, you could get the Jacobian from this expression, and you can apply the transpose on the observed data and get an image out. Again, that runs on Azure too. Okay. Oh yeah, this was a time-lapse example. So this is, since CCS is so hot topic right now, this is a CCS example. Base image, you inject CO2 into a salt dome, and then the time-lapse difference. That was from a TSET example. All right, I don't think I really want to go through the comparison. I think I just want to highlight that there are different approaches, and we had the discussion yesterday in the session too. I don't know what the right approach is. I think it's something else for everybody. Our goal for Microsoft is to make it easier for you. So whatever you want to try out, I mean, like I said, some of this stuff is already available as open source, the ZHops and the Redwood. So we put it out there. If people like it or don't like it, even then tell us so we know kind of where to go from there. Okay. Yeah, I guess the second thing to kind of highlight is that Devito is really all built around this idea of separation of concerns, creating abstractions. I think the same abstractions are required on the Azure side, plus on the geophysics side. So once you have that separation of concerns, you have all these different components. Everybody can focus on what they're good at, and they're probably going to solve a lot of the problems we have, hopefully. All right, thanks.
Thank you very much, Philip. So for the fourth industry talk this afternoon, we're going to have Ken Hester from Nvidia.
You know, I've heard a lot of great talks, and we've talked a lot about Devito, and we had a great workshop this morning talking about CUDA, but I really wanted to sort of bridge that gap between what we do today and what we see looking forward. And Devito is going to be a key part of that, and I want to illustrate how we get there. So today, with many of my great colleagues, and many of them are here today, and many of you had a chance to work with the NVIDIANs, we sort of get with you and do that really crafty activity that Alex and I myself really enjoy. We look back in our rearview mirror and say, we've written some great CUDA kernels. Like, we really love to write our CUDA kernels. But it's not something that happens in 2 weeks. Like, we put a lot of effort into that, and we get speed of light. Like, we really drive the hardware to its complete maximum capacity. We overlap memory, we maximize our MPI compute performance. We get low latency network interconnects, and we do everything we can to get the cluster to run speed of light. But as you know, for many of you, that's not really viable. Like, that's not something you get excited when you wake up in the morning doing. I have people on my team that really don't get excited about getting up and writing CUDA. I know it happens. But we do want to make sure that we're still here to help you with it. So if you want to get up and write CUDA kernels, we're here to help you. But there's some gotchas with that. Like it's not something, as has been pointed out, that you can do in 2 weeks. It doesn't happen that way. Like it's a planned activity. When you move from GPU to GPU, there's usually some activity involved in that. That's not something that happens automatically. So someone has to do the code. NVIDIA is still here to help with that, and many of you are contributing back to those ecosystems like Devito, but there's still code that has to be written. But when we look forward to what we sort of see most of our customers going to over the next 5 years, something like Devito, like where we have code that writes code. This is sort of the nirvana. We sort of picture this as the way to go looking forward, where we're optimizing the CUDA or the OpenACC code that's being generated by Devito. They've got a group of experts that are optimizing the Python framework on top of it. And all of a sudden, we have this sort of really elegant environment where we can generate and get maybe 60, maybe 80% of speed of light. And that would be great, right? For most of you, you say, well, I'm done with that. I can sort of walk away. My cluster's working well, or maybe I'm just profiling a new algorithm, and that's good enough to sort of prove my concept. But what's really sort of interesting about Devito is they gave us this thing called a JIT-backdoor. Like we can get behind the scenes, and now we can start playing with the C code. So we sort of demoed that today. We sort of illustrated that with CUDA, this sort of new backend to Devito, where we can actually begin to sort of profile that code and really see what's happening with the memory, what's happening with the cache. You know, how are we moving between our global memory and our cache system? How are we coming in and out of the host? We can really get down there and do what we call trust but verify. Because we really do hope that Devito generates the best code possible. But if I were to drop a new accelerator on your doorstep tomorrow, you might want to verify. Because there might be some code changes that we need to make. And NVIDIA is sort of here to help with that. And what's great is that we can even go sort of a step further. Like if we were to sort of take our eyes off the road and sort of look up a little bit in the horizon and start driving down the road and not really looking in our rearview mirror and sort of reliving our kernel generation past, we might say, well, why don't we use Devito to generate some images that we then train pen models with, like physics-informed neural nets. Now, using a data image isn't necessarily the best way to train a pen model, but it's definitely possible. Like we can actually do that. And in doing so, we're really looking way down the road. Now we're really taking advantage of some of the most advanced concepts and capabilities of our latest hardware. And so we sort of wonder, why would we do this? And that's literally because pen models, AI, and many of our latest chipsets, and as you probably attended some of the conferences talks here today, this week, these chips are built for AI. That's what they're built for. That's the latest generation paradigm where code generates code that generates code. So we're sort of like 3 steps away from what's happening, but the AI really, when you take advantage of the tensor cores, you can take advantage of all the aspects of having ALUs on the chips that do a lot of the computation for you. But we have a problem with using images. We have a problem with using images and pins, and that's because we're on the data-driven side of this pictogram. And this isn't necessarily the best side for a pin. We really want to slide hard left to the numerical solvers. Like we really want to drive more of the physics into the pin model. And I'm going to talk about some of the goods and bads about that. So using an image, of course, it's easier. Like we'll say, well, it's easier. Like as Devito can generate the images for you, you can capture them, and then you can train the pin model. That's great. Like we're like halfway there, right? And so we can't sort of observe the laws of physics because we program those into the PDEs that were emitted by Devito. So we sort of inherently get the physics into our image, and an AI model can sort of begin to pick up on those trends and begin to build, a complex model that can take advantage of it. But it has weaknesses. Like it's not physics aware. That is not a physics aware model. It has some accuracy problems. And you sort of see this when you start beginning to step way out in the future. You begin to see you have accuracy problems. It isn't really generalizable. And of course, we're not able to really model complex 3D geometries and curved surfaces. Like there's like this whole slew of weaknesses that go into sort of just training with images for AI. But I think we can go the next step. We have all the tools to go to the next step, which is to use Devito to directly train the pen model. Like let's bypass the image. Completely bypass the image. and use Devito to train a pen model. Now this is sort of really encouraging, right? Because now we have a tool that generates code, that generates code. Like we're on the far edge, as Etienne would say in his keynote. Like we're really pushing the envelope of generating a framework that can evolutionary change the way we sort of solve problems looking forward. And this is sort of where we want to be. Like we can continue to write CUDA kernels. We're here to help with that. And we can continue to do that hard work. But I suggest, and I sort of really want people to sort of lift their eyes up on the road, look down the road 5 or 10 years. How are you going to be solving your physics models in 10 years? And I surely hope it's not handwriting CUDA kernels. Like there's got to be a better way. And so what do we get by sort of looking at pen models? And Modulus is a framework that we have for generating pens. There are other frameworks in the market for generating pens. But Devito could also do that. Like Devito could generate pens. And it's sort of in challenge, maybe that's an intern project that we should spin up. But there's some great performances to be had. You can sort of see as we scale out with a pen model, you can now scale out from not only from 1 to 2 GPUs, but you can go out to 128 GPUs and scale near linear on your AI model. That's just fantastic, right? And so now you can really begin to grow the size of your physics models. You're not sort of constrained by your systems that you have today. And you get this sort of strong scaling effect, and you get a weak scaling benefit as well. So there's a lot of good things that happen when we go from depends for scale up and scale out, so multi-GPU and multi-node. So it really is sort of a good strategy for looking towards these large physics problems. And of course, there's some additional sort of benefits that we get from this as we look at what we can do with these sort of ALUs we call tensor cores that are on our GPUs. We talk about all of our latest generation GPUs have tensor cores. A100 is loaded with tensor cores. We get tremendous speed ups with these tensor cores. And if you get from first principle physics to pens, you get to take advantage of it. And so not only do you get to take advantage of the tensor cores where you're getting significant speed ups when we go from say the V100 FP32 to the A100, that's fast. But when we get to the TF32 using the tensor cores, we get even bigger benefits in our pen model. So we're scaling out, we're scaling up, and we're getting better performance by using the tensor cores. And we get to take advantage of things like automatic mixed precision, which are built into the frameworks like PyTorch and TensorFlow. And so these are all sort of great opportunities for us to continue to grow our capabilities in the physics space. So it's not just limited. I mean, we talk a lot about seismic. That's kind of the conference we're at. We talk a lot about seismic. That's sort of one genre of physics. But there's a whole universe of physics out there that we can actually contribute back to how we leverage and use PDEs. Like how do we take advantage of frameworks like Devito? How do we take advantage of Modulus and other pen generation frameworks to build bigger and better physics? And sort of looking across the spectrum, we have seismic imaging, seismic interpretation. I'm going to show you here in a minute a little bit about reservoir simulation. We have a talk, I think it's in a week, on reservoir simulation using pens. I encourage you to watch it. It's really sort of insightful to see that there are opportunities for us to continue to grow our capabilities. Again, not looking in the rearview mirror what we did over the last 20 years, but really looking eyes down the road at what we can do in the next 20 years. So here's reservoir simulation. So not only do we able to resolve sort of the temporal condition around the pen model, but we can actually sort of image out thousands of days ahead on reservoir simulation. Pretty critical because reservoir simulation takes a good bit of time. This also applies to things like carbon sequestration, where we're going out millions of years. Sort of think about, well, reservoir is complicated, it takes a long time, but when you do carbon sequestration, we got to make sure we don't crack the cap rock out a million years from now. No carbon can leak from the formation, right? So we really need to model this out even further, and pens are just a great way to get that performance that we need to do it. And one of the sort of the interesting ones that sort of came out recently that we were able to show is this concept of a Heuristic unit. And this is actually sort of generating savings, like they're using physics.
This massive heat recovery steam generator uses hot gas exhaust to convert water in the pipes into steam for the turbines. Predicting corrosion to avoid downtime is challenging. Reduced order models aren't extremely accurate, and full simulation takes expertise and time.
So this is all being visualized in a 3D world called
Siemens
Omniverse,
Energy
which
is
a
developing a digital
physics-aware,
twin with Nvidia Modulus
3D
for the multi-phase
collaboration
turbulent
environment
flow.
where we're using pins
With
to
point
do the
cloud
laminar
data
flow
to
of the
train a
water.
physics-based AI model,
So this
they
has
can
real
infer
effect on
high-fidelity
their
flow
ability to
shown by the
actually generate
streamlines
and
in
maintain
seconds.
the
This could reduce
surface equipment
downtime by
unit of the person
70%,
unit.
saving the industry $1.7 billion a year.
So there it is. It's saving the industry $1.7 billion. Not possible without the pen. And it's because we had to think outside the box. Now, did NVIDIAns get involved in that? Yes, we generated a lot of code that trained the pen model. But that's where we take advantage of frameworks like Devito to do exactly the same thing. There's plenty of opportunities for us to use it, not only in the fields that we're in, but really to influence those that are around us as well. Thanks.
Thank you, Ken. So for our fifth talk this afternoon, we're going to move to academia, and we're going to get a talk which is going to be presented by Matthias on behalf of Matthias and Felix Hermann. So Matthias Louboutin, take it away.
Thank you. Yeah, so that's the last talk. Thank you, everyone, for still being here. And so, yeah, we're going to switch a bit more to the academic side. And so I'm going to talk a bit about our work on building abstraction on top of Devito to really enable research. And since we are academic, like one of the main concerns and the main goals is actually adoption by industry, our technology and our research, and being able to develop the right tools and the right abstraction to make it really easy for industry to just try our software and try our new algorithm easily is one of the main goals to really improve collaboration and adoption. So there is a lot of names on that slide. This is basically the people at Georgia Tech, Philip Witters that used to be with us. Gabriel is now at Utrecht University, who is working mostly on medical imaging and things like that. And there is probably a few missing names, but yes, so this is an effort that we've been working on since 2014, 2015, where we moved towards Julia because of once again, it's a great abstraction that allows to have very clean and easy code to use and to transfer to people. So some motivation. So we work on a variety of problems as part of our research group. As you saw on the previous slide, we have people from electrical engineering, we have people from earth science, people from computer science, and so we need to work at different levels of working on physics, machine learning, linear algebra, optimization, you name it. And so managing the complexity of all these different fields is a lot easier if you build the right level of abstraction and the right software to handle all these different levels of complexity. And so we built up numerous packages. I will briefly mention some of it. And we also build on external packages like Flux in that case and ZHops that are machine learning packages to really extend the reach of our research. And so this abstraction and this different level of abstraction are really, really important for, at first for innovation so that we can develop easily technology and validate that technology without having to spend 3-4 years or half a PhD writing a new code that may or may not work, usually not work. And, and of course, reduce the costs and once again, improve and make it a lot easier for industry and people to adopt our technology. So our software basically sorts in 3 categories. So there is Judy and Judy for CUDA that Philip mentioned, so which is a linear algebra abstraction built on top of Devito that makes everything extremely clean and mathematical so that you can easily develop optimization problem while still relying on Devito for high performance wave propagator. So of course, Devito we've been contributing to since the beginning. As you say, I almost get lost in London. Gerard didn't want to let me go.
You already set my house on fire. Okay.
Yeah, I did. Don't let a Frenchman in your kitchen. And then there is Invertible Network, which is a machine learning framework that was started by Philip. That is built to work, for example, on normalizing flow and a lot of machine learning applications that you may have seen at the ACG and EAG, for example. So the main idea behind Judy, so that's the Julia Devito Inversion Framework, it's a simple name, is to build a linear algebra abstraction. Coffee, the Chevron people have a similar framework that is based on JET, where you can define linear operators that represent your wave equation, your receiver interpolation, and everything, so that you can very easily, in one line, write how to model synthetic data, how to compute an RTM image, how to compute image volumes, or anything like that. And then under the hood, it interfaces with Devito that is still implemented in Python because, well, it works perfectly in Python, so we didn't see any need to rewrite it in a different language. And Devito then generate and compute the wave equation as needed in high performance, on your cluster, in the cloud, everywhere you need it. And so this abstraction leads to like extremely simple algorithm like this one. So this is a very simple least square RTM. So you can see that like you can write in about 10 lines a sparsity promoting least square RTM that actually leads to extremely good image. Like a code like that in an industrial code would probably take about 5,000 to 10,000 lines, and I'm not even sure they would be able to fit a curvelet transform in it. So this allows us to like run this imaging like in the cloud in 10 lines and actually play with like these different algorithms. Like, do we need sparsity? Do we need TV constraint? Do we need multiple constraint? And we can actually run that in about, like you can run like 10 of these a day on your desktop or on a cluster just because you have this very simple, concise code. And on top of it, so we actually wrote a machine learning interface to it so that we can actually use this linear operator as a neural network layer and actually backpropagate and run automatic differentiations through it because we actually have this high-level abstractions that allows us to define these adjoints and gradients. And so this allows us to do algorithm like this loop unrolling LSRTM. So this is an algorithm where you actually train on pairs of like true image and RTM images, and you train through a full so unrolled RTM. So like this J would correspond to like iteration, and then in the middle of your network you have this J transpose J, which is going to be a demigration migration, followed by a standard neural network and an activation function, and then some linear algebra. So you can really combine absolutely everything together. And because you have all this layer of abstraction and definition, it just works out of the box. And that's what exactly the Julia code would look like. And once again, you have in 10 lines something that like you would probably need even more lines just to write it on paper. And finally, the last level of abstraction, and so Philippe introduced it, is that how do we actually run that in the cloud? Because I know that like we saw a lot of talk from industries that have this like very nice 10,000, 100,000 cores and all this hardware. We have access to one desktop at the university and some cycle on Azure that Azure graciously gave us. So we need to be very efficient with it, and we need to be able to actually run things in the cloud cleanly while still being able to like abstract this part away so that people can still do their research properly. And so this JD for cloud is, so Philippe showed it a bit, but this is basically a little wrapper on top of Redwood that basically hides away all this Azure batch parallelization and like even this YAML files that's actually automatically generated through JD for cloud, so there is no YAML file in this one. And then all the linear operator and the GD definitions stay exactly the same, and it then just actually runs it on Azure when you actually need to like generate synthetic data or run an RTM. And so the initial proof of concept for this like serverless approach, so this is something we did in 2019. Philippe and I were sent to Redmond for 3 days. They gave us $10,000 of Azure credits, and they said we want an RTM by the end of the week. So we ran an RTM on Azure Batch, and so we actually got a TTI RTM within a week because we had Devito. So the code actually fit in 10 lines, and the only thing we had to care is that how do we actually use that Azure service, knowing we have this beautiful tool that is Devito that's going to run anywhere we just send it. And so we were able to get this RTM image that we presented at the Azure HPC workshop, not workflop. And so once again, through the abstraction in this JD for cloud, you get the exact same algorithm, which is once again just 10 lines, and you get sparsity promoting least square RTM running in the cloud without any change to your code. It's just standard Julia code that you can run on your desktop. You go home, you come back in the morning, and you'll get your RTM on your desktop. And so you can even run like much fancier imaging. So this is TTI RTM run on Azure on GPUs. So this is cheap GPUs. These are M60 because that's what we get access to. So these are GPUs with 6 GB of memory, and you can run TTI RTM on it if you like actually take advantage of Devito the right way. You don't need a terabyte of memory. And you can even get subsurface common image gather if you want. This once again ran fully serverless on Azure with 4 gigabyte of memory without any serialization or anything. This is just a linear operator on your desktop with everything hidden away with the right level of abstractions. And finally, as I said originally, one of the main goals is interoperability and like industry adoption of our technology. And so through our development, we made sure that everything we develop, our software, our linear operator, so Judy and our optimization framework actually is compatible with standard Julia code. And that actually makes it compatible with any software that a company would write, such as Chevron. So in that little one, we combine Jolly, which is our standard linear algebra package, with JETs, which is Coffee equivalent. And so you can basically build a linear operator for an FFT in Jolly and combine it with a circular shift operator in JETs, and everything runs just with standard multiplication as you would expect it from linear operator. And as you expect, like it passes like all the dot test and everything because all the operations are correct, compatible within a mathematical abstraction, which means it's by definition, you are not forcing people to interpret your software as it just works as the abstraction defines it. And so another example is just some FWI where we combine basically everything we could find. So we have our optimization framework. We plugged in the Chevron propagator, and then we have this set intersection projection. That is a software that computes the projection on intersection of sets. So you can have a TV constraint with like a box constraint with a minimum rank constraint and put everything together. And so you get your FWI result with like the work from like basically like academia and Devito and Chevron and everyone, and everything just runs out of the box. And so when you actually take all of that together, it actually allows us to work on like even more complicated problem. And so this is a problem that is quite recurrent these days, which is carbon capture sequestration. And more importantly, we are looking into how do you actually monitor carbon sequestration via seismic. And the main idea is to have, through seismic data, being able to model and invert directly for the CO2 concentration in your sequestration. And because we have all this abstraction built together, including automatic differentiation through like neural network, we can plug in a Fourier neural operator, we can plug in any like convolutional network. We could add some physics-informed neural network if we wanted into it. And so we can actually invert directly from seismic for the CO2 plume in the reservoir so that we are able to actually monitor almost in real time the evolution of the carbon. So some final observation. I try to show like through these talks that like if you actually build the right level of abstraction, not just Devito, but even on top of it, and make sure that at every level you're giving the right interface and the right tools to the user, you can actually build extremely complex framework that are like literally plug and play, so that you can replace one piece by someone else's piece. If like, for example, someone comes up with like a new propagator, you could like replace Judy by Coffee, you could replace our Fourier neural operator by like Nvidia's physics-informed neural network. And you can make all these pieces play together like in a matter of weeks so that you can immediately figure out what works best and how you can get the best answer for the most efficiently. The best answer efficiently. Sorry about that, it's late. And so it allows the coupling of physics and optimization and machine learning, and it really allows collaboration and better development in general, because now you don't have everyone doing this little research everywhere and no one knows how to run it. You have this openly accessible and usable research and software that allows really for better usage of resource, I would say. So that's it for me. And I guess I'll give back the floor to Ami.
Thank you very much, Matthias. Thank you. So the last speaker of this session is going to be Gerard Gorman, representing Devito Codes and Imperial College. And I think this will be the last talk of this session before we'll take a break for coffee and refreshment, and then come back for the panel session. So hand over to you, Gerard.
So I think I would be derelict to my duties if I didn't start saying thanks to everyone, okay? And I don't mean just because of the workshop, but specifically, we have to think, how did Devito even come into being? It's exciting, I'm passionate about it, because I think there's interesting science and everything there, even in terms of computer science and exploitation of a lot of knowledge and expertise and know-how that's been locked away in the compiler communities, and it's been completely siloed. This is a trend towards actually pulling it in and making it accessible to applied domains such as this. And in terms of, for those that don't know the story, so one of the reasons that Hamish McIntyre here is chairing the session is he's the person who actually made this happen originally when he was in BG Group. And I still a bit unclear the details, but the idea was, the full wave consortium, yeah, they could do with your help, doing some HPC and improve the performance of the code. And that somehow migrated into managing to convince Intel to give us a suitcase full of cash to implement this entirely new technology. And in fact, it was the largest donation that Intel did for any project, and all we had given them was a blank sheet of paper. But it wasn't entirely this big risk. We were copying other work that had gone on previously with the compiler team. So this was Firedrake with finite, that was focused on finite element. And largely, why did we start wanting to create this thing? Well, we wanted to create this thing because it was sheer murder, having to edit hundreds and sometimes millions of lines of code just to add a term to your equation and say, goodness sake, there must be a better way. And they had already proved out, this technology that it worked for finite element, and if it works for finite element, there was a good chance it would work for finite difference. And it was indeed, say, Fabio, who's the architect, really the architect behind Devito. He did his PhD on the Firedrake project on the finite element and could bring all of that knowledge here. But then the other parts of the dynamic is that was that sort of the money man, and then it was bringing in that partnership with hardcore computer scientists or compiler specialists. And then the other part of it was well, how do we think about this in the right way? Very often, if you're not thinking about the problem at the right level of abstraction, the right way, with insight into the physics and the mathematics, you're doomed, okay? Because you'll just implement loads of code that's in, turn away. And then that's when I met Felix Herman, who was my first conversation with him. Was I answered the phone in my office, and I had someone yelling down the phone at me about something that I shouldn't have chosen Python, and I needed to think about abstractions. And then after about 10 minutes, I got a word in edgeways to say, yeah, I agree with you on abstractions. That is really the key idea, and that is the thing that needed to be nailed. And I think there's very few people in the entire community, who really understood just how vital that is. I think it's probably fair to say, so I'm a blow-in to this community. I only really joined right at the birth of this project. But I think Bill Symes is the other person that really had a keen understanding that it was abstractions were absolutely fundamental to get right. And indeed, like the very first EAGE talk that I gave, he came up trolling me afterwards and said, yeah, that looks okay, but how are you handling boundary conditions? And I said, yeah, we haven't done boundary conditions yet. But that was right at the start. But again, but the point is, he knew how to think properly in terms of abstractions, get the abstraction right, and everything comes out. And then, so I could ramble on for absolute hours, but what's the point that I'm trying to drive at here? Oh, well, then I have to say Doug. So Doug are not here with us today, but it was quite important because think about it. Like, say I was going to conferences, everyone thought I was mad. So they say, oh, well, we're developing this tool, it generates code automatically, it will save your marriage, walk your dog. People don't really buy it. So how do you actually develop trust? And then one of the other issues as well is if you're in academia, very often, like academic code or research code is actually a code for crap code, or like unverifiable, unmaintainable, not usable code. So you're up against that. So Doug then was an important first step for us, because that was our first opportunity to say, well, okay, convince someone to actually use it commercially. Forget about academic papers, that's fine, but that's still academics. But actually put this into production where someone has to pay the bills. And then that was that was a whole other level then for us to learn what it took, in terms of understanding the features. Oh, we need this feature, that feature. It was always something different. And then that was another evolution of about a year, just to be feature complete, so that it could actually be used commercially. And since then, now we're part of a much wider community. I'm usually appreciative to all the industrial talks. And pretty much everyone I spoke to at the conference from different oil majors and service companies are using it, trying it out, not always talking to us, but they're trying it out, and that's really exciting. I can personally say that my professional career, this is the most satisfying experience I've ever had in terms of actually translating ideas in theory into something that people are actually using and getting stuff done. That's what it's all about for me. And lots of fun people to work with. Oops, wrong button. Too many computers. Now, what this talk is not going to do, as I ramble on, check the time, I'm not going to give you a Devito talk. I think it was much better that other people gave Devito talks. You've already been at workshops. You already know enough. But just as an opener to lead into other stuff, so currently, what is our current feature set? So, supported backends. So, of course, we start off with Intel because they're the guys that originally paid the bills. And then everyone was trolling after us, saying, yeah, that project only works on CPUs. So that's why we were really keen, to actually get into GPUs, just to say, no, this is a general idea. It can be applied to other architectures. So that's, we're in good shape with GPUs and Nvidia now. With I need a drink of water, but okay, goodness knows where I left the bottle. But that even shows up some interesting stuff. So we pretty much have pushed OpenACC to its limits. We pretty much know we can't extract any more or very little. There's very limited how much extra performance we can get out of it. And now, very recently, we started adding a GPU backend. And again, say in terms of, I think everything about Devito has been a story about communication and relationships and people actually speaking with each other, accept a certain amount of modesty in terms of understanding that, okay, I know this, I know a bit of your stuff, I'll try to understand what you're talking about, and then that collaboration to get something working better. And this is exactly what we're iterating on now between Nvidia and Azure in terms of having that active cycle again, in terms of test, point out what's wrong, update the compiler, start generating new, faster code, profile again, and just keep moving on to the next problem. And I think the important thing here is that I don't really, it doesn't trouble me in the slightest when Ken, Ken is a really polite guy, but he came up to me yesterday and he was there, oh, well, do you mind if we show this? Because if we profile it, it doesn't look so good and I don't want to make it look bad or anything. And this is maybe the biggest culture shock for me when I got into this community is, Friedman, everyone wants to be very secretive and not admit when there's a problem or to look at something. When in actual fact, the benefit of this framework is exactly, you say, well, yes, this is what the issue is. We say, oh, I understand what that issue is. We know how to fix it. You fix it, and then it's faster. So even when there is a problem, it's transient. So you're monotonically advancing towards better performance or adding features or whatnot. But again, you can actually design, just simply with a bit of modesty and a willingness of trying to understand what other people are trying to explain to you, understand other people's specialities, you can basically engineer, progress forward. And a few times throughout this talk, I'll be just waving my hands. This is not a complete list. There's a very long list of other stuff because with new features and whatnot coming through. But I think it wasn't really useful to go through it exhaustively. But then to harken back to a point that's made on earlier in the week, people, there is a tendency. So I'm someone who has always been passionate about open source software. Right from the beginning when I got into computing, in the 90s, I was always very passionate about it. I've only ever worked on open source code for my entire career. More or less, small fractions where I was contractually otherwise obliged to. But there's something to understand here. People and people that are maybe new to open source, to just imagine. This was a talk the other day when they were talking about it was the morning session, the panel discussion, and they were saying, oh, we need to introduce some open source at this layer for distributed computing on the cloud because that will fix anything. No, but just labeling something open source doesn't magically fix all of your problems. And I think we just have to be, which I'll talk a bit about later on. But that's okay. It's a case of, it's part of the solution, but we just need to get a bit more sophisticated of what other ingredients you need to actually make this work. Kind of like a pizza, open source is like your flour, but you need a bit more than just flour to make pizza. And this is a segue into why we had a startup, okay? And I'm trying to be careful here. I'm not trying to shill. I'm just trying to explain the rationale, because I feel as well, as sort of the principal investigator, first of all, I also have a responsibility to my open source community, okay? Say we had really formative collaborations that continue with people groups like Felix Herman's, where they have made massive contributions. So among others, so we have an important responsibility to that community. So when we move things forward, we need to talk and explain on why we do different things. So we started Devito Codes about a year or so ago. And it's so the question is, why did we do it? So if you're a company, I'll talk more about this. The first question you should ask, if you're even vaguely a sane person and you're building a product or you're running a company, or even if you're developing, let's say, a research agenda, you should be asking, well, is this something I can depend upon? Is this a software dependency I can afford to have? Is it going to be around, in a few years' time? Already, there's a lot of hidden investment. If you actually think about it, one of the things that frustrates me is a PhD student, if they start working on a project developing software, you're talking potentially about 4 or 5 years investment of that person's life developing something. So you can't, so you really should be thinking about, well, they're doing something, they're betrayed for something, they're developing software. Is it going to be around? Does it have any longevity? And if you're a business, if you're going to start building, say, for example, I was very excited to hear that Ion Geophysical, sorry, like started building on top of Devito. Like very excited about that, but I'm very sure that their managers were saying, well, like, you know, we're taking a big punt on this. Is it going to be around? Like, say, are you going to see, like, you know, maybe not me, but maybe you'll see, are you going to see Devito here at Rice in 2032 or 2040? So the question is, well, the outcome, presumably if you've made the investment and you're using it, the outcome, you would assume that you would expect to see it. Like that's the outcome that you want. But if that's the outcome that you want, you better plan for it. Okay, we sort of get the future that we invest in or that we plan for. So an observation. I put in most, but like if you do a bit of googling, like, you know, it's very hard to find exceptions to this rule, that most sustainable open source projects are ones that spawn a sustainable business to support on the side. Because, and if you look in, there's quite a lot of literature on open source business models. And like one of them, for example, is the so-called sugar daddy model. And that basically is like TensorFlow, for example, falls into that category because you have got large company that's very cash rich, and they make the business decision of supporting that open source project, okay? And then a lot of the big open source projects that we talk about fall into that category. And any other one, it's because there's another startup or some business that has some way then of generating revenue. Because say other projects are trying to say 100% open source, and if they have a commercial end, frankly, other people move on. They might move on to a different project. You're unable to pay the salaries of the core developers, and like, you know, like 50 other things go wrong. Okay, so this is primarily seen as a mechanism to support a core team. So again, like this came out of university, but you cannot run something like Devito. Like it's already very sophisticated, has a very high threshold in terms of the quality. Like you can't do that just on PhD students, like say that are coming and going and returning. It's not McDonald's. Like we're not cooking burgers. Like you need to have a core team who have that core expertise, who can basically who can train the next generation, even of engineers that are coming along to do further development. But also for a company needs maintenance and support. Like, so if you want to service a broader community and get people actually using the code, at the end of the day, a company is going to want to pick up a phone and ask for support when everything goes to hell, or things are not working, or they're worried about the next stage. And the fact is that this is not something that fits well within academia. Not at that academia, and this is basically one thing I'll emphasize later on. Academia, that's for research. And then, but like service, and like, you know, commercial enterprise is for a company. But you can use the commercial to invest in the research, which is so. That's our route to sustainability. And again, this is not something that we have made up on the fly. Again, it's about sort of reading what's successful open source projects and open source business models. So the next question is how. So that's the why, like, you know, what motivated us to start it up. In terms of the how, and I think this is an important point as well for our community. We fixed on, after doing quite a lot of research, we focused on applying an open core business model. So what's this mean? So the principle of this is that you keep 95%, or like choose some number, okay? We can quibble about that later on, but you basically try to have the maximum amount possible open source. Because again, you're going to die if you don't have the community. You're thriving on the fact that there is a community, that you have got researchers, you have PhD students, and so on and so forth, and you have got companies developing it. Like you've now got companies contributing open source as well to this. So you're trying to maximize that. And frankly, like, you know, not to be too blunt about it, you're largely keeping back to 5%, because if you don't do that, no one will pay for a license. They'll say, well, because you're all cheap. but pragmatically, that's a big part of it. So I have had loads of conversations, and literally, like people say, yeah, well, I was trying to convince my manager, but they won't fund this because it's not clear what we get out of it. So because they don't get something out of it, that they can go back and report up the chain in terms of like something that comes gift wrapped or whatever. And they will say, well, what's the difference between if we don't pay for it or don't pay for it? And then the outcome is people will happily use it, but they won't pay for it. So this is bad. So this exactly, this is a threat to our sustainability. Ergo, the 5%. Now, part of this then is, so we were very careful, as I said, like, I've been involved in open source development for more than two decades. So when we originally started Devito, I've basically made sure that every contract that was ever signed, like say on the research side, all had open source commitment there. So we were fine in terms of liabilities and warranties. And that's the way that we're continuing forward. So everything done on our on the academic side remains open source, and like Felix Herman's group as well at Georgia Tech have taken a seminar. So again, maximizing open source, again maximizing what the community can achieve. And you can see as well, like one of my pet hates is people say, oh, the project is open source. And what you see is all the development is done behind closed doors, and then once every 6 months they push some stuff to GitHub. And that's not what happens here. Like all of the development is open on all of the open development is done on Slack. You're all welcome to join it if you're not there already. And we actually go as far as we can in terms of like, as soon as we submit a paper even to be reviewed, that's my own team, we actually just stick a preprint on archive as well. Like, so again, it's a case of, like, we show our stuff, we're happy to show our stuff, and we want people's input on it. Now, in terms of this model, I think the last impression I want to give is that we have all the answers. I think anyone that, it would be stupid to think that I've got all the answers. So I think there's plenty of questions. Maybe that will come out the panel. Maybe it'll come out over beer later on or whatever. But there's obviously still some things that need to be worked out. But the important realization for you guys is, like, you shouldn't you need to understand that, like, you're part of the community and you need to be actually feeding in to actually let's explore and figure out what the answer is. And sometimes there isn't a perfect answer. There's a compromise between multiple objectives. But again, I think this is what's I hope as we go forward in the future, we'll introduce a bit more structure and figure out how we actually get proper town meetings or some type of governance structure in terms of like helping to advise and to steer decisions in this regard. So, plenty of questions. Yeah, this is definitely one of those areas where I have many more questions than answers. Again, I don't want to shill, okay? So my intention here is not to shill Devito Pro. I want to be clear on that. But the obvious question is, like, what kind of things are currently in the proprietary version? So this is just to illustrate some examples. So like data streaming, so you start needing this for 3D, that depth bounding box. So so the balance that we're trying, this is our first attempt at getting it right. We're not claiming we're perfect, but hopefully with discussion with the community, we will get it pretty good. But so the balance we're trying to get then is we don't want to slow down researchers. We want to basically do everything we can so the research and the open source community, the research community, are unencumbered and move forward. And then, but what is the actual bits and pieces of stuff that you need if you are an oil and gas major or if you're someone that's actually running this to make money? And again, it's not supposed to be exhaustive, but it does. And now, in terms of the roadmap, I added and deleted about 50 slides this morning, okay? And I think this is there's a lot of exciting ideas. A lot of people are doing some incredible stuff. We've got loads of wish lists. There's a lot of stuff I'm passionate about pushing forward as well. But I think there also needs to be this, if you care about this or you think that it's useful, you also have to remember that open source doesn't actually create magic money trees. So we always have to link, in other words, if you want something and you want to make it happen, then you're going to have to think about how to invest in it and make it happen. So after adding loads of those, after adding lots of slides and deleting them, I was thinking about what I wanted to say, and I know I'm going over time. But I thought the right thing to do was maybe to, state the obvious, which is obviously the CUDA stuff is currently what we're having the most fun with at the moment, and we all want to see going forward. But then I thought I'd just like to highlight some of the early career researchers, the PhD students. If I'm going to name someone, I prefer to name the PhD students. Some of the things that are coming through that I think are quite nice. So one, of course, George, so he's been helping out, where is he? Yeah, so he was helping out at the training. He's the guy that set up all of the VMs for the training as well and made sure everything was running smoothly. So he's been working on time tiling. And I think this is pretty awesome because people have been publishing about time tiling forever, but there's one catch. Okay, if you put time tiling into your code, good luck to you trying to maintain that code. That's why you don't see it in production codes. So his dissertation, and he's writing it up now for soon, right? And that it's about automating all of this so that it's actually automating in the compiler the creation of time tiling. So do that with source receivers. So there's the only other group that I know actively working on this is in Kaust. But yeah, you really have to think there's a really good reason why this is not in production codes, because you're talking about level of optimization that just humans are not going to maintain in the code. But this is sort of the true automation. This is the advantage that you have. Immersed boundary conditions. So that's Ed Cand. So he was where are you, Ed? Oh, there. Didn't recognize you. That's immersed boundary conditions, so for doing land surveys. So this was a request that came in. When I first heard it, I said, oh yeah, that should be easy. We use immersed boundaries in CFD for years. We discovered it's easy maybe for a special case. Generalizing is a bit more hard. So, and you would have seen Ed's poster outside. But we think this is a pretty awesome feature, particularly when it is generalized. So land surveys and so on and so forth will require this. Then getting away from that, like CFD, so Kenny, where's Kenny? Hey, Kenny. So Kenny was helping out as well this morning. So this is a nice departure because also we were looking that, and this maybe I'll take the opportunity to clear up on a bit of confusion earlier on. I mean, that I got earlier in the week. People are saying, oh, well, we had a bit of a criticism of Devito because I don't like their implementation of PML. I was like, well, the thing to understand is that Devito is not what's inside the examples directory. What's inside the examples directory is just some examples. That's why it's called the examples directory. Devito is a platform for you to write PDEs. You can write whatever goddamn PDE you want, okay? And I think this is... and I think that's really an important distinction, okay? Now, we might do something different, but then that's going to be and I'll mention this later on, but that will be a different repo, and it will have different sets of dependencies and so on and so forth. But all Devito is allowing you to write finite difference, solve whatever PDE you want. But the CFD is interesting just because that's forcing as well to start adding support for implicit methods and iterative solvers. So that's going to be that's interesting from the technical as well as pushing it into other areas. And brain imaging, we're very pleased with this as well. So Carlos, of course, is not here. But we were when Mike Warner's group published the paper in Nature, they said, oh, we need to go at least 20 times faster or so. But when we integrated the Devito and we ran it, we already got to 20 times, and that was even not before optimizing the GPUs. So that was very satisfying, and it's nice. There's more and more people now on Slack are turning up. They're doing brain imaging. So again, it's nice that you're seeing the power of abstractions in generality. If you name, as Felix was shouting at me back, right back at the beginning, get the abstractions right. If you don't know the abstractions, it's all going to fail. And you were right. A little further downstream then, so they're the active PhD students. Like finally, the UK decided to actually fund a research program specifically targeted at exascale software. So it blows my mind that it's so hard to get funding for developing software, even though reproducibility of science and so on and so forth, it's not like we don't depend on it. So we were funded as one of these projects. So these were targeting strategic codes and technologies in the UK that they wanted to carry forward. So we were very pleased to be part of that. And specifically as well, like there's two objectives coming out of this. Like, well, there's a lot more in the proposal, of course. But like one of the considerations, working with this team, thinking about, well, like what can you lift out of this and generalize in terms of these types of DSL, the compiler technologies, where you could, to make it easier to develop new DSLs. Okay, so that's pretty CS, but also then emerging architectures. So Cerberus then is written into it as well as a work package. So I was really interested in the talk from Total yesterday from Mauricio, wasn't it? So looking at, like, say, how we add even another backend. So it also nicely illustrates, like, doing something more exotic in terms of the hardware. So this is a pitch. This is unfunded, like, you know. So any of you that have got change burn in your pocket, like, you know, let me know. But I think so. And again, in terms of the roadmap, lots of things in and out. But I think, frankly, like my experience over the last, like, you know, days, maybe weeks, is that this is probably something that the community needs. We should figure out how to create it, because it actually takes a surprising amount of sophistication on the part of the user to know how to like just deploy a code on HPC. Like if you have to worry about affinity and so on and so forth. But also then going into other considerations like, say, PDEs. People do, like the community does want a catalog of properly verified implementations of every PDE known and so on and so forth. So this was something that we started and then we sort of shelved just because we were busy doing other things, but we'd like to get back into it again. And it requires a combination of actual infrastructure, because all this thing relies on code verification and CI and everything. So it needs to be running in the cloud, it needs to be live, it needs to be reproducible. But there's also then like optimization. So for example, like can you fetch, like Oracle, like, you know, can I fetch, how exactly should I be running the code when you're solving this specific equation on that specific architecture? And currently there isn't a solution for that. So we think we have something. We're discussing it with various people. And I think that maybe the ultimate, frankly, is maybe to establish some type of community. So you could imagine, they've done this in machine learning, for example, where they've established community benchmarks and gold standards. Everyone submits their benchmark there. They can have dance-offs against each other. But, like, you know, how do you actually establish the equivalent for the seismic community? So we're also discussing this with Azure. So please bring this up if this is interesting. And closing remarks. Well, as always, I ramble on for much longer than I should. I think the most important thing here is, like, say, like we have to work together. Like, so I think I really like John. I keep mispronouncing his surname. John Edgen's talk from BP. Like, say, I like the fact that he highlighted that we were basically stagnating as a community, because frankly, like, say, every advance that you're trying to make It's just hardware. Everything is getting freaking harder. So you're just trying to, I just want to add a term to my equation. And it's getting harder and harder to do that in terms of learning CUDA, learning everything. Nothing wrong with CUDA, but the point is, my God, I need to have 10 PhDs just because I want to make a relatively small advance in terms of technology and science. And that is fundamentally, like, that was the central thesis. That's problematic, like, you know, because then you're having to slow down in terms of advancement. There's a big risk. But the irony is that true specialization is the answer. So here what you're really doing is it is hyper-specialization, but it's just like architected specialization so that it's you have specialists then able to interact with each other, such as the Devito core team interacting with the Nvidia team to make it go lightning fast on their hardware and so on and so forth. So the bottom line is, yeah, think about it. Like, say, this is not our project per se, it's yours, and it will be what you make it. You can Google for, yeah, GST. Candor. We encourage candor.
So thank you very much, Gerard. So we're going to have, a panel session that will maybe take as long as we still have energy. Till closing, and this is your opportunity to put a question towards the speakers from the earlier sessions, and for to try to stimulate some more discussion about how we want to take the Devito community forward. So since this session has been recorded for those that are not here, I encourage you to make sure that you speak into a microphone when you have a question, and Paul's going to be walking around the room with a microphone. So just as one last point of introduction, or to continue the conversation that Gerard had before the break. So thank you very much for the kind words about, to me, for the initiation of the project. But then there's one person who's not with us today who was also very influential in forming the Devito project at the beginning, and that's my colleague when I worked at BG Group called Charles Jones, who now works for a company who's putting seismic data in the cloud, OzoKey. But he was instrumental in realizing that we needed a tool like this to future-proof our research seismic code. And it's between Charles and I that formed the idea of this project. So I'd like to thank Charles as well. Okay, so let's move on. So could we have maybe the first question from the audience to start the session going? And please suggest, if you've got a suggested person you'd like to answer the question, then also please mention that. Any questions from the floor?
I can make a comment.
No, you have to phrase it as a question.
John.
I'm not on the panel, so I have a comment, I guess. I think at the end of your presentation, Gerard, you said something about this idea of some sort of benchmark. And I love the idea of having reproducible algorithms that you would submit to this benchmark. They'd be run with CI, and they would have like a fixed budget in energy cost or something, and you see who gets the best FWI result. Now, that doesn't tell you necessarily much about performance with respect to Devito, but that's an idea that I think is really cool, and we could maybe do that through Devito, where Devito would be the underlying engine that does the propagation. Just wondering if there's any thoughts on that. Since no one else said anything.
I think you're exactly right. So we did have a prototype of this put together. So this was to give credit's due, I think primarily Rodri, we hooked everything up through GitHub Actions to create the whole sort of architecture of this and getting it deployed on all different hosts. So we used on-prem cluster. So we had basically stuff running all over the place. And it does allow, because the key thing is reproduce, freaking benchmarks. It actually is quite hard to do proper, very well controlled, reproducible benchmarks. And then simultaneously then to document the damn thing so that when someone else tries to do it, how do you do that? So I think with that prototype, I think it has all of the ingredients because there's the scheduler we're exploiting, GitHub Actions, and then containerization, and then the tweaking, and then it's only, in my view, there's I nearly use the word just, but the engineering, the information is there then in terms of Docker files, JSON files to extract out, what was the parameters for setting that up.
Yeah, cool workshop.
Yeah, and then hang it. Yeah, like so. And really because we see this the whole time, like because this is not the job of it's not a fault of our software if you run this on a new architecture and it doesn't magically pin, right? There's a very good reason why process pinning and affinity is not part of the OpenMP standard or whatnot. Like say this is more of application level. But also, like it starts getting pretty esoteric, or like the geophysicist just wants to run their damn problem. And I think we could look then at just sort of introducing this other layer, and I think it could be just basically one infrastructure, but it would actually satisfy a lot of different requirements. So we've spit around lots of ideas, like for example, set up bounties, like say $1,000 for someone to give me this bloody PDE and adjoint of whatever variant of TTI you want. And how many PhD students would have that knocked out pretty quickly, trying to get $1,000, and then have it verified, correct? And all. But this is what is possible.
Yeah.
So you want to collect your money already?
Felix Herman, Georgia Tech. I think it's a great idea, benchmark. So people do that in machine learning community all the time, and also medical ultrasound. And I think we can do this for wave simulations for one shot. But you can't ask universities to run 3D TTI RTMs that cost $10 million to run to make a benchmark. Right, so that brings me to the bigger concern, right? So I think what I admire in what was happening with Devito, and but what concerns me a little bit is we create all these cool codes, but we can't run them, at least not in academia. So I don't know how I can keep my team engaged if we can never run in 3D FWI. We don't have access to compute. So I think when you say benchmarks, you also want to benchmark on real problems. We can't run the real problems, and I think that should be perhaps part to the discussion somehow, because Devito is being developed in an academic environment. I don't think you have ever run in 3D FWI or RTM yourself, right? Yeah, I'm talking you guys.
Like the overtrust. Of course, there's only Mickey Mouse.
Yeah, Mickey
box.
Mouse. Right.
Like, I think Google paid for it. What did we do? Blow 100 grand in a week for them?
Yeah, so that's the only thing we did. And then Azure was kind enough to give us one run. So we got $10,000. We ran one RTM. That's the only 3D thing we have been able to run at scale. And I think a lot of people don't understand that's the case. And I think that I see as a long-term threat towards sustained development of open source code in academia. So
yeah, so maybe I'll comment on that. I think the industrial personnel in the room, they should really be thinking about the fact that we're probably burning cycles, maybe not indiscriminately, but not as efficiently as we might be, and that maybe that's something we should think about to bring cycles back to the academics if we want them to work on these kind of problems. Just a thought, right?
I can't guarantee that my graduate students would be better at that than people at Shell, but yeah, it's a great idea.
It's something to think about. I think it's it's a point of discussion.
Yeah.
We still process massive 2D data sets, and there's a lot of value in 2D processing. And I think from a geological perspective, you can get a lot of insight from 2D. And in academia, I mean, I was running 2D elastic FWI codes during my PhD almost 20 years ago, right? And so
I could run MATLAB Slash on 2D on my laptop.
Yeah.
There's no challenge there, right?
You mean from computational?
Well, I mean,
yeah.
Develop scalable algorithms in 3D. That's a different world.
Yeah. Yeah, but I think a lot of the theory carries over. So, and maybe it's something we can talk about afterwards, because I think there's a lot of probably spare cycles floating around. And maybe this is speaking for my personal, for me personally, rather than as a representative of my company. But hopefully, maybe if we come up with better ways of scheduling stuff, we could. It would be nice to think that industry could maybe help out in other ways.
I'll echo that since we got TGS talking here, or not TGS, and this is not talking ion, but there are spare cycles, and the main hurdle is accessing those spare cycles because people worry about, like none of our data centers are set up for multi-tenancy, etc. However, in one could set something up in terms of if you guys have something that you want to run and truly try out, get us the data, get us the code, we'll get on a team session or something, share stuff, and we'll kick something big off and let it run for a while. I think that's, in terms of industry, that kind of model is probably the easiest way of getting at cycles. The other thing is, I don't know how many public cloud representatives are left here. They should as well. And I mean, all the big three, of various levels of big, and then a couple of others may very well be interested to chip something in, because it's peanuts for them, right? So I would hunt after that.
We did. And a lot of people are trying to get to their cycles, and it's not as easy as you think it is, unfortunately. But I let Philip.
I mean, I think there's a little bit, often the conception just because Microsoft sits on a lot of hardware that is just sitting there, and doesn't matter if I use it or if I don't use it, nobody uses this, so why don't you give it to me for free? And I mean, I'm sure we would love to. I mean, I don't know if I speak for Microsoft, but I mean, it cannot obviously be only the cloud provider, but it cannot only be industry, so we should find some kind of consensus on that. I agree. I mean, we try to get academia credits where we can, but it's not as easy to give somebody $1 million for a run. I mean, unfortunately.
No, certainly, but it's actually a good point. There's also a triangle thing that one can do with if there's an industry partner with a cloud provider that has a relationship, and if then a relationship develops with academia or with spin-offs from academia, that one can work out a triangle deal there. And I do think some of the business development managers at the cloud providers are interested in that kind of stuff.
Yeah, to come back to the cloud provider, there is also a separate level of issues that raise for academia working with cloud provider and industry in general is, even so we do get access, as Felix says, that we did get some credits from Azure, there is a different layer that we are still academia, which is like, even so we do get credits, we do not get the same access to Azure as the paying industry is. So like we've seen all these like beautiful results on like A100. We don't get access to A100, even if we ask for it and we have money for it, because they are reserved for industries that are paying. And so now you end up with codes that are still nice, but it's like, that's not the hardware you are, so why do we care about your performance? And so it still makes it a bit hard, because there is still that separation of like access, even if like the credits are there, like the treatment kind of you get in terms of hardware and software and support you can get through these providers.
Yeah, and I think that's probably where this triangular kind of agreement might bring some solutions. I think we should maybe move to, well, a question.
One more point to that. I used to be working in the academic world as sort of like the HPC provider internally in the university. And we had both university supercomputers, national supercomputers. And basically, the research methodology was there to request a grant for compute hours. I assume there's still something here in the US as well.
Not geared to this sort of stuff.
Well, I think you can
Why not?
request it from TAP.
You can go, of course you can go to the Department of Energy, other places, but they're not used to give you 1 million CPU hours to just run an RTM. They're used for a very different model. They like you to develop code that you can show scales, and then you write a paper and you move on. They don't do regular working with data, trying new algorithms, the whole sort of workflow that you need in order to create seismic images. They're not used to that.
And there is also a lot of dedicated resource. For example, at Georgia Tech, the largest cluster they have is an NSF cluster. You are only authorized to use it to run MRI. You can't run anything else on it because it's part of the grants. And these grants are extremely dedicated to one problem. And so that makes it extremely, and this hardware is probably not running all the time just because it's so specific that people don't have stuff to run on it. But I mean, it's probably used most of the time, but it's...
My experience is that academic supercomputers are 99% full.
Yes.
And the only 1% is for management of the system. So then it's down.
No, I know. I mean, we used to have a cluster at UBC when we still had only for it. So we had, 56 nodes, something like that. So yeah, it was running non-stop, but yeah, it's...
Okay, so maybe we're going to move on to a different subject. I mean, I have a question for Chris to bring in the discussion, and that is, I guess, what stopped you putting production code on Devito? I mean, you showed some nice examples from intern projects, but what were the blockers? Because I think that's something we should talk about because we can maybe understand where we need to put some effort to get uptake.
Sure. A few blockers. Well, definitely the initial lack of GPU capability. Okay. So when we first looked at it 3 years ago, we were interested in validating some of the CPU claims and understand where the technology was headed. But we've been making highly optimized GPU-only code for the last 15 years now. So it was very unlikely we were going to crowbar some CPU propagators into there somehow. And more recently, it's probably something we should be trying. It's something, there's a significant amount of effort crowbarring it into our scheduling engine, making it work properly with the rest of what we call our feature set, what are the other things that go on in these propagators. So yeah, part of it was waiting for functionality, and now that functionality seems to be pretty much there. The responsibility is now on us to see if we can make it work in our processing code and see how that goes.
Okay. So I mean, is it? I guess one thing I'm wondering is it a lack of information or clarification of what's possible in terms of the feature list at the moment, or or it really was just sort of early? You were on an early take up, right?
It was early take up. Again, I'm dancing around the performance questions quite a lot, but part of it is the performance gap.
Yeah.
I mean, and that is closing. If there's orders of tens of % performance difference, yeah, sure, maybe it would be a great thing to put in there, especially for things we haven't developed in house. But if it's 10, 20, whatever it is, on the GPU, whatever that performance difference is, we need that to close a certain amount in order to take it seriously in production.
So if it's 10, 20, there's a bug in the...
Yeah.
There's a serious problem.
Sure. That's why I shouldn't have thrown out any estimates out there, but yeah.
Into the microphone, please. Oh.
Hey, Paul, just 1 second. I think it's really critical if we think about what I presented earlier, which is we've spent 15 years hand writing those kernels. There's endless number of man hours involved in tuning those kernels so they run absolutely speed of light on their hardware. And it's going to be very difficult to have a code that generates code that's going to match that performance. And so sort of to step in and to replace it, well, we have to change the functionality. There has to be a whole new algorithm that they want to run that would make them switch off of their current code base and go to Devito. There has to be some other driver other than saying we can generate the code now.
Ken, can you publish benchmarks for one of these that you say is speed of light for a well-known physics like TTI?
We have samples that we write to speed of light that we write.
I mean, can we set up a public benchmark where we know exactly how fast these things operate on a particular size problem?
I think we generally publish our numbers for sure. It code's almost public. Yeah, it's almost public. There's always a lawyer involved, I know, but yeah, it's almost public.
John, to answer your question, the problem comes down to: do you have the same kind of codes? Right? Is it really? It never is the same. Starting with the stencil size or other boundary conditions, whatever. It's never exactly the same. And then how satisfactory is the answer? If you say, well, it's the same. It's TDI, but right. And how important is the but? Sorry, that was... the other thing to add to what Ken just said is the work that Luke and John are doing is not to replace our existing RTM code, for example. That is written, well, we think very optimally, right? It's produce new work. So one reason why that is maybe not at the same production level as our production code is because it's new, right? It will be. I don't have no reason to believe that it can't be put in production. Sure. Definitely not the performance. There are other things, sure, there is, people are nervous about that. Oh, that's using open source software, we can't use it in production. There are probably people that think like that, but the main thing is that is active development work. And over time, if it gets to the maturity level and everybody's happy with it and whatever has to be done to make code production, then it can be production, absolutely. It's just a timing thing.
Yeah. So here's another question. What is your roadmap for auto-tuning, one? The other is profiling of the generated code. And if you can connect the high level, say, Python or physics level down to the architecture that the code you generate for the particular architecture, given the fact that you have so many different targets, you must have a way to connect this operator or this style of computing at a high level. This is the performance when I map it to, say, a GPU or to a CPU. So you should have this semantic connection between these two levels so you know how to optimize. And when you profile, you can provide enough information for people to realize where the problem is in the code you generate. So what is the roadmap for auto-tuning and the profiling architecture?
So that's a good question, very good question. So one of the strengths of Devito is that you user, you give the mathematics, then you got this compiler that allows you user or you even developer, to generate, to synthesize different implementations. Semantically equivalent, but different. So to me, when I develop the compiler, I do it such that, so I know that all those versions, they differ. In what do they differ? So they differ ultimately in the operational intensity. So in the amount of data you move, for example, because you're using temporaries for mixed derivatives rather than redundant computation. So there are a few trade-offs that we know to be important ultimately for performance. There are not too many. There are a few. And so we got a model in the compiler to create this space of possibilities, yes, of code synthesis. So when it gets to auto-tuning, so basically it gets to trying not 100, not 200 different versions, but 4, 5, 6 versions. And if it's someone like me or Matthias that have played with this kind of kernels for like years and through the compiler, we sort of know already from the beginning where we should go. So I'm not sure if this answers your questions, but all I'm trying to say is that eventually we have the knowledge to create a space of solution that is not unbounded. So it's bounded, it's limited, we know how to explore it. It takes time to develop, the search algorithms to get there, but that's, our approach.
Do you report back this information so the people who write the high-level codes, do you report back this information so that people can make the connection that if I use this style of coding or whatever, okay, at the high level, or as move down to the levels of abstraction, where how I can fix performance problems and actually, how I can get best performance out of different architectures at the bottom.
So just to clarify, for us, the auto-tuning, so the tuning, the profiling, so that's not Devito. That's a system on top of Devito that exercises Devito trying to find the best point in the space of solutions. So yeah, you user can get some feedback about what Devito. So you run the tuner, and the tuner tells you you should run Devito with these options to get the maximal performance of this kernel on this architecture. But that's all you got. What we love about the interaction with NVIDIA, for example, is when we have to build new points in this space. That's crucial. That's the game changer. Because they use the JIT-backdoor, for example, that Ken was talking about in his talk, to tell us, look, your code is doing fine, but if you actually do that instead of this, you also get, you get this little bump in performance. So then we translate that knowledge into the compiler. So that's the kind of feedback loop that we...
And if I may jump in there, that is, to me, as somebody who, at least at some point, wrote CUDA kernels, that is the more interesting interface, right? I want to be able to measure performance, and then I at least have the ability to go in and say, okay, what is it doing? And is there, for that particular case that I have in mind or that I'm trying to optimize for, is there something that I can do better? Not necessarily better than NVIDIA, but better for my use case. I think that is the key part, right? The user, the everyday user, John shouldn't have to worry about that, right? John should put in his PDE and trust you to get near optimal performance, or optimal enough in that sense. With zero time. Or
Maybe we'll move on to another question. We've been patiently waiting.
No, I had a comment on the production use. So we are literally weeks away from internal production release of RTM and FWI with Devito. I know we haven't been that involved originally, but we looked at everything. I looked at the JIT-backdoor very, very early on and looked at the produced kernel. I was like, oh yeah, that looks all right. And we liked the idea. And just in terms of performance, can the best vectorizing or CUDA gurus get faster performance? Yes. But in the grand scheme of things, in the end, we're after time to solution. And that's where Devito wins hands down. And that's why it's the path forward. Even if we lose 5%, even if we lose 10%, I still think we come out ahead.
Can ION publish their performance benchmarks when you make that release? Like, throughput for a particular physics? Would you be willing to do that?
Not on the first release. We got to get a little bit more. Sorry, yeah, you got me there. Also, we're mostly a CPU shop.
That actually put my numbers up there. I'm nervous now. You guys must be like 20 times.
you should be, because you probably didn't ask your boss whether you could show it, right?
That's why we really, really like John.
And now keep in mind, we're also predominantly a CPU shop. So our numbers are going to be significantly lower than what other people are doing. But in the end, it's the result that counts. And we do firmly believe that we can get very, very good geophysical results out of Devito with very little developer effort and really being able to push the physics and get good results out of it. And that is something that ultimately may be more important than just raw speed.
Yeah, we agree.
One completely other question, and that is, I've been sort of like playing around with Devito, very limited, but having fun, sort of like finding out what the tunables are. My question is, when I'm trying to run this on a reasonable large scale, we did sort of like the 100,000 cores run. My question is a little bit, what should I expect as the output from Devito? Should I expect sort of like the demonstration we did here with the container running and providing me sort of like a number? Or should I actually use the JIT-backdoor and pull out the source code? Because that's the one, that is the code that is going to create my binaries in the end. And that is what I want to integrate in my flow further on. I definitely see sort of like the research and development context right now from Devito. I cannot I don't see the path forward to how to integrate this into a large-scale production.
So
I'm not saying that it can't be done. I've done it. I've done it. I just see sort of like, I don't see the reason why I should be doing the just-in-time compiling each and every time of the same code on 1,000 nodes.
You don't have to do it 100,000 times. Right? You can do it once per job.
Yeah, and do I use the JIT-backdoor to pull it out, take the binary, integrate it with the rest of the code? I mean, I don't see it in the context of Devito yet on how that flow.
So there's maybe subtleties to your question that might be missed by people. But yeah, like you can imagine if you're using the Intel compiler that has using FlexLM license, and like the last thing you want is 100. Huh? But either way, like say you don't want 100,000 instances of compiling the exact same thing. So there's a bunch of strategies. So like I can't share exactly what they are, but there's a bunch of obvious things you might do. Like if it's just once, like yeah, you might one process compiles and then does a scatter. In reality, like when this is in production, it's compiled once. And then like then that's then bundled and like already distributed, pre-distributed. But that's when you already know, because you're in production, you shouldn't be recompiling the thing that never changes ever. And there's several other flavors. Like the great thing about sort of software and technology and stuff is we like if you don't like what it's doing, you change it. Like so like someone else then said, well, I really hate Python. And it's like, well, fine, like, well, when you form the operator, like, you call C interface and you get back to C and the header files and integrate it whichever way you want. And I think we have to have this, and I think this is why, like, discussion and feedback is important, because it's technology. Like, we can morph it and redesign it, like, to facilitate different use cases. But yes, I share your allergy for redundant work. We don't like that.
I will make a comment there, though.
Sorry.
If you don't run 100,000, well, actually 100,000 cores would still be fine because there are only 10,000 machines. For most of our work, we don't bother doing. We don't bother doing any pre-compilation because the amount of work that you end up doing for a proper shot with a proper seismic aperture is in the order of minutes at least, if not more. And taking the overhead of once on program startup, even if I keep redoing it in all instances as they come up, taking, 3 seconds to compile it, it's negligible. So we didn't even bother with it.
But I still need to distribute gigabytes of my compiler to each of
yes,
those.
no,
So there are a lot of problems that are being triggered by it.
Yeah, just to comment. Also, just to comment concerning the JIT-backdoor, this is not meant to be a production tool. This is a tool we built as a feedback loop so that we know what we need to add into Devito so that it produces proper code. So the aim of the JIT-backdoor is not to be used in production. You're never supposed to actually look at the code unless you're trying to improve what Devito generates, so that the next time you don't need to look at the code. But you're not supposed to look at your code in production. It's supposed to generate the correct code like initially, because you did all the work on your desktop on a single tiny problem with the JIT-backdoor to know what to do in Devito to fix any issues in the code generation.
I have a quick question right here. I'm Wei Chanley from Aramco Research Center, Houston. This is more of a research side, not on production side. From your point of view, has there been any issue between abstraction and customization? And is there any suggestion for, say, if people take this trend to customize, especially on the efficiency side, what are the recommendation guideline you would offer, say, certain, I notice you, for example, you can change different, at a certain stage that's outside the abstraction level, you can apply different modification, but at the core components where you are covered by the abstraction, or there's any potential people can take that, customize it, and if they try to do it, any guideline you would offer to maintain the level of efficiency you have. Thank you.
Like, it's very hard to speak in generalities. Like, it's much easier, because nearly the answer is nearly always it depends. But I think right from day one, like, and this is a conversation I had as well with Chris earlier on, like, say the consideration is, why is there so few DSLs and why has there been so many failures, like, in terms of stuff that has gone out there? And has been this disconnect between, like, say, computer scientists developing DSL and then, like, it actually being used in a domain where you start having all of these engineering concerns to actually do some real work. And I think then from day one then, like, when Devito was being developed, it was being developed with, and this is what Matthias was referring to as well as the JIT-backdoor. It was always developed with a graceful degradation in mind. So there was always a backdoor, like, from day one. And this proved, proved super vital, because we're always, well, it's inevitable, even though it happens less frequently now. And like you discover, okay, I need this other feature, but I can't quite do it yet because it's not yet there in the abstraction yet, or we haven't quite figured out what it is that we want to do. And it always sort of gave that route then that's like, someone could go in and hack it and make it work. And then but that cycle then, it's like that innovation cycle then, that's basically telling us from experience, oh, that's what they're doing, and then we can, like, it's an anti-pattern, like, so this is classic software engineering, it's an anti-pattern, and then we can study it until it becomes a pattern and then extend it. So I think this is, so number one, it's a backdoor to let you in and get your work done, but it actually is also a feature that's one of the things that allowed Devito to evolve so quickly. I don't know if you want to say anything on that.
I think you guys got it perfectly. I mean, so Hugo, so we maybe this is our fault. Maybe we should try to explain this better. So, but the JIT-backdoor is not meant to be used in production, as Matthias said. So I developed it because I needed something. So I developed the compiler, so I had to understand what the compiler needs to generate in a certain situation. I needed something quick, so I came up with the JIT-backdoor. And then I realized that what I had done was something that could have been potentially useful to other people as well. To Nvidia, for example, to new users. Basically, it's a dev tool. Yeah, and maybe I can add that. So the only reason that today the JIT-backdoor is a viable tool is because the result of a design choice that we made 5 years ago. And the design choice was that we were going to generate human-readable code, for which we spilled quite some blood. And so now you can see the code that Devito generates. And yeah, without that, I mean, maybe you can use it, but you wouldn't be able to understand what's going on. There are other DSLs. Well, some of you might have heard of MLIR in TensorFlow, but good luck with that. It's like assembly. So, I mean, I prefer to read C or C++ than assembly.
So we have a question here.
One of the things, I know there's been talk about the compilation at runtime and how that can be an issue, but something that I've been throwing around, and I may be completely off base with this, so this is a great time to correct my foolishness if that's the case, is you get the opportunity to perhaps perform arbitrage on the spot market for virtual machine instances, because you can, suppose you have some benchmarks and well, give or take on this certain machine, this is how many dollars I'm paying for a gigacell of wave propagation, right? I more or less know ballpark numbers. So if I just sit around and I set like a limit buy, saying, okay, I'm willing to pay this much money for wave propagation. I'm just going to sit here and only run wave propagation when I can find some sort of machine that's below that threshold. And you'll get, a Frankenstein cluster out of this. But with Devito, it doesn't matter, right? Like Devito will take care of all of that. And so I'm wondering if you think that that's like a reasonable way to approach this problem and perhaps perform some sort of cost savings.
I'm glad then you liked the Devito matrix pitch that I did during my talk. But that's exactly one of the things. And we've talked about it as well. I see Hugo raising his hand. But it's this is a no-brainer. It should be implemented. I think we need to get maybe a few interested parties. Well, we've already now got a cloud provider and an oil gas major, so let's make it happen. But this is a no-brainer. This is exactly what you should do, and then you just you're basically able to say, do you care about price of solution or cost of solution, and then you're actually dealing with hard data, and there's no. So it was an interesting question from again back at John's talk. At start of the week he would say, what's the impossible problem that we should be thinking about to start going to solve? So that problem you talked about there is not one of them. So we can do it. There's engineering. We should just go ahead and do it because it's just it's a no-brainer.
So can I disagree?
Yes.
So I think going back to what John Etchen was saying, is that what we want is specialization, right? What I want from you guys is to give me a finite difference operator that runs efficiently on a large suite of hardware sets, and that's my problem. Okay, so Chris is saying, okay, his developers can beat you on his hardware type, and hopefully ours can beat you on our hardware set as well. But we have a card. Well, when we go to the cloud, we actually find that our cost performance metrics are actually different, and our conclusion is different. Ken shows up at the door and says, here, have 10 new XYZ cards, right? And then we're supposed to benchmark them, right? But you actually change the card, you have to spend a year trying to optimize your card for that card type, right? So what I'd like to see from you is actually, I'd like Ken to give you all his A10s, A40s, A30s, A100s, whatever the next generation of cards that may or may not be coming, and get the CUDA guys to help you guys optimize your code on all of those cards. Let us know what the price performance is so that we can make the right, so that when we go to our cloud provider, we don't need to try and optimize for all these different systems. And the cost optimization, I think that's a different abstract layer, because I don't care about cost optimization for the RTM. I care about cost optimization for RTM, 4D reg, 5D reg, SRME, all these other algorithms, and I want my abstraction for cost performance to be solving, to be a different abstraction. I want it in a different set, because I want to make sure that it's going to solve all of my problems for all of the different types of workloads that I have. And so I'm not sure that you guys are the right person to solve that problem. I know you're the guys to solve, well, I hope you're the guys to solve the problem of optimizing finite difference wave propagation across as many different hardware types as possible. And I think that's where the value is, because we might be able to beat you on one type of GPU, right? But then, yeah, across the whole, it's like, I don't know what cards these guys have, but someone's got an AMD GPU floating around somewhere. Our most cloud providers have at least half a dozen different types of Nvidia GPUs. We can't keep up. So that's
maybe I can jump in there and offer something in the middle. I think what Devito can do, in my opinion, is help provide scalability to solving that problem, right? Because if we all do it, first of all, Ken has to go to all of us and give all of us one of those GPUs, or whatever it is. And well, it happens, right? That is how this works. We all know that. But then we all have to go in and test that card and figure it out how to make that better. And well, some days we're lucky and figure it out, and some days we're not. But it does cost a lot of time, not just Ken's time, but our time. No offense. But I think there is, and not as the only solution, but I think as a proxy halfway in between, if that work can happen between, you know, let's say Nvidia and Devito, and then also Microsoft and AWS and whomever, because they all add their own flavor and they're all obfuscation layer, if you like, on top of that. I think that is where something like Devito can tremendously help. Not to solve the problem completely, not to produce the one best performing code out there, but to get us close enough that we can either say, oh yeah, that's good enough, or as a starting point to then further optimize that. But basically, we have one party that can do most of the work so that we don't all have to do it.
Yeah, no, I think maybe we're all agreeing. I was just thinking like it'd be kind of neat if we had an abstraction layer that basically went, okay, I'm going to take this type problem and try and optimize it, like work out what the cost performance of it was on different hardware sets and optimize like VM shapes and things like that. And I'm not sure like that's actually would end up being quite a big problem. And I think having a different specialization team looking at that problem would make more sense. But just looking at like how an RTM runs, yeah, absolutely. I think seeing results from you guys would really help us.
Yeah, I wanted to say two things, I guess. One, I think this last discussion was great. It plays into the comment I made earlier about how there's this big collaborative opportunity, and it's a collaborative opportunity. The other thing is I'm a detail guy, and there's two details about this just-in-time compilation thing I wanted to mention. Number one is there's a non-negligible impact if you factor in the temporal and spatial discretization when you do that compilation, right? The code gets faster, the throughput improves if you do the compilation just in time and factor in the discretization. And number two, Fabio's waiting for some sponsor to say, make the compilation time faster, right?
Yeah, we already know this is true, actually. We do a lot of just-in-time compiling on many different GPUs. That's what we do, right? And what we noticed along the way, particularly in the last couple of years, but particularly with Python, is that if we JIT our CUDA code that comes from Python just in time, it runs faster than if I precompile it. And it's because at the moment of JIT, I know more about the host processor, the buses that sit underneath it, and how the GPUs are interconnected, that I can actually make some really intelligent choices on how I compile that code. Things that I can't do if I compile it early.
Or if you're compiling for 20 different architectures, right?
Right, so if I sort of back it way off to something like an SM50 architecture from a few years ago, I'm not going to get anywhere close to an SM80 architecture. So there's some things that we can do that help you get the best out of the hardware you're on. But that's what we're hoping to do by working through Devito.
Yeah, can we make the compiler a little bit smaller?
No, I don't have any control of that. I don't have any control of that.
Yeah, with containerization, we could do with something less than 10 gigs from you guys. 17 gigs.
It could be my lack of skill in building Docker containers. I will definitely brush up a bit to see, but I've been trying to do the compact, and it's not squashing.
We don't need latex.
Somebody.
Sorry.
I have a beef, and I want to say it right now. Somebody in Devito is putting LaTeX in the notebook. That's all I'm saying. Like, someone's loading it up with some bloatware.
So maybe we'll take a question from Rob here.
Yeah, thanks, Hamish. I wanted to add a comment on what we care about, right? What I care about at the end of the day is what it costs me to run RTMs, FWIs, etc. I care a lot about gigacells per second and stuff like that because they're indicative and they're a step along the journey, but they're not the end game. So when we look at where we need to land with these things, a lot of it comes down to what else have I done to get that turnaround time? And it comes to a point you made, Alex, somewhere along the way. Nothing is apples for apples. I have seen over the course of my career more steps made from things that aren't changing the gigacells per second than the things that touch that. Right, so we've got to think about the big picture and what we're actually trying to deliver. I think Chris has covered most of our positions on this, although of course we were on the journey and there is more to come. And no, John, I'm not going to publish the numbers as soon as we've got them, but we do need to get a better understanding of where we are and where we're going to go next. I think I would anticipate we will have the heaviest workloads with all the things we do, which will run well in terms of gigacells per second, and really well in terms of the final product. And until you can compete with that final product or give me a faster journey to that, that's going to be one of the challenges. We'll also have very specialized workloads where we run, Chris alluded to it, 1 or 2 jobs. Yeah, great. There's no way we can hand optimize all of those. So I think we've got to really lay out this whole landscape and understand it. And I think one of the challenges is, knowing that, Gerard, from your point of view, how do you help us get that ground so as many things as possible go into that latter category, and we're left with 1 or 2 specializations? And I'm delighted to hear, JJ, that you're well on that journey already. And I think we will be on parts of that as well. I just can't predict exactly how that will play out. But I think it's that balancing act of how do we get from optimization to the thing we want to deliver.
So I think that's in play. It's collaboration. It's actually fundamental. So I like the phrasing of your question, like trying to figure out where we want to end up. Like if you don't know where you want to go, like you're definitely not going to get there. And even during the week, for example, it seems like that very few people had run, say, the Nvidia profile on Azure. That's not a problem. The point is, it's an experience. Like say, people work together, shouted at it until it worked. Finally you go find what the problem was and got it working. But then that's just part of the whole sort of life cycle as well. Then in terms of performance. So Ken has already given us, it was Florin that generated a list. Here are the things that need to be fixed in the code. Now, I think we agree that for performance on the CUDA. Now, they're all very straightforward things to do because everything is just, if we wanted to, you can walk to Washington. It's just a series of small steps. But then the point is that the infrastructure and the methodology and everything is there and the partnerships are there. So what's going to happen? We'll complete the next 2-3 steps of performance. It'll start generating new code. It'll be thrown over the fence again to Florin or one of the other, Ninja, Nvidia developers or whichever the vendor is, and to say, okay, to give us that next level of insight. And because these guys, they speak fluent Silicon, and you really want to tap into that, Uber's specialist knowledge and and be modest to say, well, what can be done? And then actually have the infrastructure in place that when they give you that knowledge, you're actually able to make use of it. And the really powerful thing then is you're not doing this for one code. A question I'd like to ask, like you said, how many man hours were spent handwriting lots of different codes? A question is, so we are where we are today, okay? So we are already used by quite a few companies. We're in a good place in terms of adoption and everything. Say the investment so far in Devito is order 2 million. In its entire history. But let that sink in. Say if you think any one of you, say you'll be much better placed than me to estimate what your software development costs. So to implement all of the solvers that we currently have and so on and so forth, put a number on it. So that's why I mentioned as well to Chris. I'm less concerned today. It doesn't stress me out when you say, we're not as fast as our code. That actually does, it used to stress me out, but it doesn't stress me out at all, simply because, what we know is that we're monotonically, approaching that point. All we need to do is continue working together.
And I'll just point out really quick that I've worked with many people in this room, or at least my team has, and not to call anybody out in this room, or let's say it's someone not in this room, but the first time we look at someone's code, there's many codes that run slower than Devito does today when we first look at them. Right? That's computer science. And so we work with how to get that to HPC. And by the time we're done with that code, it's running significantly faster. We can get there with Devito too. It's just us training Devito on how to generate that code. So a little bit more time, you'll see things like compression inside the kernel. If you want to take of it a lossless or lossy compression, GPU direct for storage, completely bypassing the CPU in general. So that helps when you go to these lower end ARM processors, so you don't have to invest so much in your host system. RDMA support directly out of the kernel, going out the backside of the server for scale out architectures. All of these things we do for codes today, we can actually embed in the code emission or code creation that happens inside of Devito. We're pretty excited about it. We have a pretty aggressive roadmap that we're trying to do on our side for Devito this year. Hopefully we can actually get enough of their time to actually get it all done. But that's all for you. That's all so that you can actually be able to use those tools to generate algorithms and see how we might do it if we were sitting behind Devito.
So can I add something to that? So I've been thinking about to say what I'm going to say, because if I say it, I might sound a bit too defensive. But if I don't say it, I know I'll be going home thinking that I should have said it. So I'm going to say it. So that's the premise. So.
Yeah, maybe you need to whisper to us first.
So going back to what Chris was saying 20 minutes ago, roughly, about the performance, I'm with you. I think that ultimately performance is crucial. And I do get that you guys have spent a significant amount of money, rightly, over the years, to get maximum performance on GPUs, for example. I get it. And so I get it that if today we try to do an apples-to-apples comparison between what we generate, you fix the physics, generate it with Devito, then you take your code in-house, we do a comparison, maybe, I don't know, I'm guessing, maybe yours goes 30% faster on a V100. Maybe not, maybe yes. So I'm not concerned about that 30%. And to be honest, some of you have said that there's a gap, and that gap might not be filled by Devito. I don't believe that. I think that with enough resources, that gap can be closed. Because at the end of the day, clearly with the help of people like Ken, for example. So at the end of the day, it's all about understanding what's going on. And once you understand it, it's all about translating that knowledge into the compiler. So if there's that 30% gap, why is it not closed yet? So it's not closed because it's all about the resources that we have at our disposal. So how many developers in Devito? So there's a bunch of PhD students that they've got to do their research, like George, for example. We cannot ask them to do the core dev. So there's basically me at Devito Codes, and then there's Matthias, who is invaluable, beyond invaluable. So if we are in this room today, it's also thanks to Matthias, absolutely. But he is an academic, so he's got to write papers and all sorts of things.
Takes way more time than Devito.
And then we look at the pay that ultimately. But so just to conclude, then we look at the people who pay the bills ultimately, okay? And they come to us with a list of requests, and those requests are not just about the performance. That could be the compilation speed, like John was saying earlier. That could be, like I was talking to JJ yesterday, and they are not our customers, complaining about a potential bug in Devito. So we've got various issues, various requests from people, and then there's people who want compression on GPU, and then serialization, all sorts of things. And those things take time, take some time, and but we are limited, so we are finite. So
give us money.
Also, I want to add something else, because otherwise I'm not sure I'll remember to say it later. So all these projects, so my belief is that, okay, we've got Devito Pro, open source, it's all beautiful, blah, 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 fantastic. But this is not just about the software. So this is about building a platform to bring people together. Potential hires. So that, to me, is even more important than the software itself that we are building. So you get people together, you get brilliant minds together, you can do beautiful things. So that's the way I see it.
Can I ask a hard question? And this is for Schlumberger and Ion and Shell. Who plans to support this new consortium, this new open source business model? Can you tell me? And JJ, I just heard your name. I don't know you well enough to put you on the spot like this, but do you guys plan to support the open source business model? You do, great.
In the works.
Outstanding.
There's lawyers involved and things like
Yeah, of course, we know all about that. It's taken us a long time. Thanks.
Yeah, no, I just want to say, like, to come back on what Fabio said about potential hires, there is a reason, like, Google is throwing that much money at PyTorch, because they don't need to train people when they start working for them. And it's a lot cheaper to support PyTorch than to spend, like, 6 months training people to use your own internal software every time they start, and to learn how to, like, work with it. Because PyTorch TensorFlow, they show up, they run it within a week, and they have new model running. So that's part of like that investment that goes into like open source software. And so,
yeah. I'm going to make another comment about the performance thing now too, which is, I think we're entering a phase soon, these are my own opinions, where the 10, 20, 30% is less of a concern because these A100s are so fast and now have so much memory. There's a lot of other things we have to do to try and keep up with them. Like compression is one of them. A lot of these cloud SKUs don't come with enough terabytes of SSD to really keep up with a lot of these wave fields and things. And so suddenly, you know, there's a game change with a lot of these things when it's not just cranking out the gigacells a second on the GPU. It's also having to play a lot more tricks with these actual node shapes and understanding the fabric. And even then, every single job is different. The output grid, you know, the points per wave field you have to propagate out, all these other things. So yeah, don't think I'm just sitting here waiting for the 10, 20, 30% to close. Like, there's a lot of other stuff going on.
I just want to add really on that point, Chris. I mean, that's really the key in what I'm saying is there's so much more to it to get there. And, you know, what I would really like to see, and we've had this discussion before, Gerard, is that we really do start figuring out how do we help keep things moving along, bring new features as they're relevant, things that we've done that help performance that you perhaps ought to build in once. You know, there's a lot of them that I know JJ will be doing in their code, so there's not a lot of point in hiding them any longer, and we might as well start bringing those so you can capitalize on those as well. But I think Chris's point, just to emphasize that, is getting the most out of these things. There's a lot of dimensions to it, and by the time you've gone through all of those, it adds up. And we spend quite a lot of money on compute, so percents do matter. But it's not just the percents at the pure propagator in terms of cells per second, it's the end-to-end. And, you know, we are fully behind the principle of what you're doing here, and we just need to figure out how we help out. And, you know, to answer your question, yes, absolutely, we want to be as involved as we can be. We just need to figure out the details along the way.
And to add to that, maybe turn that into a request to you guys. Make sure that you keep the scope, not just on the, and I know you don't, but don't just keep the scope on producing a kernel that runs fast. But if that, for whatever reason, strips our ability to integrate it into a bigger workflow or take care of the I/O or whatever it is, then that loses value pretty quickly. So, you know, this JIT backdoor is a fantastic idea, but it needs to be so capable that allows for tweaking all these other things that Rob just alluded to. That especially because this is not finite difference modeling, right? This is RTM, this is FWI or something even bigger yet. And there are absolutely a lot more things to that make a much bigger difference in some cases than just the flops. So keep in mind that the scope is bigger. And then I can already see Hugo asking the next question. Also keep in mind that there is other things beyond that, you know, orchestration and so forth, that then kind of are the next level that need to be. Maybe that's not all on you, but keep that in mind, right? Keep the focus wide enough so that can grow and can still remain useful beyond just the kernel.
So let me add a little bit to this, because I think what my group has been adding to the whole Devito is the geophysics through Matthias. I think also people may have noticed that we actually built geophysical applications that use these kernels to bring the state-of-the-art in FWI and RTM further, with the sole purpose to actually reduce cost. It's not only in how long it takes to run a wave equation solver, But you can do lots of things that make the cost of imaging way cheaper. We have done that successfully. I think Schlumberger uses internally a stochastic sampling technique we came up with that led to 7-fold reduction in cost of FWI, making it a profitable proposition internally. Ask Dennis Wieck that, and he will testify to that. And so that was solely something that came from my group. And so when Jared asked for money, I'm also asking for money. Because frankly, I spent quite a lot of money to get Matthias to do this work, and I have to get that money somewhere. And there are some people in this room sitting and not paying the bills. And that has many facets, not only the sustainability for code development like Devito and all the things around it, but you're also not training the next generation of people you may want to hire. Because Matthias made a wonderful point, right? If people are used to Devito, they will also be tempted to work with you if they can continue in a real industrial setting on Devito. And you have then a chance to actually get them before Google gets them. And so there's an enormous good case to be made up in management to actually support groups like this. And I shouldn't have to plea for this the way I'm doing it now. It's frankly ridiculous.
I don't want to make light of what you said, but can we hire Matthias?
Well, then
can I stay home?
Okay. If the code he writes is no longer open, then half of the production of video will be out. You will not make many friends in this community.
So I think we should probably draw this to a close, because I suspect it takes about 15 minutes or so to walk over or to get to the Hungry's location. So I'd like to thank everybody very much who was on the panel to take these questions. So if I can ask you to thank them. And thank you all the contributors for a great workshop today, or parallel workshops even. I thought it was an excellent and successful day, so thank you everybody.